The universe, a vast swirling canvas filled with mystery and wonder, holds more secrets than our minds can fully grasp. From the delicate and intricate dance of planetary bodies, each in perfect harmony, to the bizarre and unfathomable anomalies that push the boundaries of our understanding, the cosmos beckons us to look deeper. What lies within the dark, unknown recesses of distant galaxies? How do alien worlds challenge our perception of life itself? The universe invites us to explore, to push the limits of knowledge, and perhaps transform the very way we see the cosmos. As our scientific understanding advances, there are still several celestial phenomena that continue to confound even the most brilliant minds. One of the greatest mysteries is dark matter. Despite making up around 27% of the universe, its true nature remains an enigma. Dark matter does not emit light or any form of energy, making it invisible to even the most powerful telescopes. Instead, it can only be detected by its gravitational effects on visible matter. It seems to be the hidden framework that holds galaxies together, yet what it's made of, or how it came to be, remains a question that eludes us. What is this invisible substance that influences the very structure and behavior of the galaxies, and why is it so elusive? In tandem with dark matter, there's another cosmic puzzle that intrigues scientists: dark energy, a mysterious force responsible for the accelerated expansion of the universe. Dark energy accounts for nearly 70% of the total energy content of the cosmos. Unlike matter, which clumps together to form galaxies and stars, dark energy appears to have the opposite effect, pushing galaxies apart. This enigma raises profound questions about the future of the universe and the fundamental forces that shape its very existence. What is driving this accelerated expansion, and what will be the ultimate fate of the universe? Could dark energy be the key to unlocking answers to the most fundamental questions of cosmology? Fast radio bursts, another captivating phenomenon, have captured the attention of scientists since their discovery. These brief, intense bursts of radio waves travel across immense distances, and their origins remain a mystery. Some hypotheses suggest that fast radio bursts could be related to neutron stars, highly magnetized remnants of massive stars, or even be a signal from advanced extraterrestrial civilizations. However, the true source of these signals remains elusive. The search for answers to these mysterious bursts continues to be one of the most exciting and active areas of research in astrophysics today. Equally puzzling is the behavior of supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way. These colossal objects can contain anywhere from millions to billions of times the mass of our Sun. Yet the precise mechanisms behind their formation and growth in the early universe remain largely unknown. What we do know is that supermassive black holes play a pivotal role in shaping the structure and dynamics of galaxies. The immense gravitational pull they exert affects the movement of stars and gas within the galaxy, creating a cosmic ballet that is both awe-inspiring and complex. As matter spirals inward toward these behemoths, it is pulled into a dense spinning accretion disk, a chaotic swirl of gas and dust. The immense gravitational forces generate powerful radiation light, which not only illuminates the black hole's surroundings, but also triggers high-energy jets that can extend across vast stretches of space. This process, known as active galactic nuclei, has far-reaching effects on the evolution of galaxies. The radiation and energetic particles emitted by the accretion disks can heat surrounding gas, creating powerful winds that influence the formation of stars and shape the galaxy's future. These interactions alter the density of interstellar matter, inhibiting or even halting star formation in certain regions, while igniting new bursts of creation in others. As a result, supermassive black holes are not only central to the structure of galaxies, but may also hold the key to understanding their evolution. Each of these phenomena, dark matter, dark energy, fast radio bursts, and supermassive black holes, represents a chapter in the ongoing cosmic story. Together, they fuel the scientific curiosity that drives our exploration of the universe. With every discovery, we uncover new questions, pushing the boundaries of our knowledge ever outward. And yet we remain only at the threshold of understanding the vastness of the cosmos. Each mystery is a beacon, guiding us further into the unknown, inspiring new generations of scientists to look up at the night sky and wonder, what's next? What lies beyond the veil of what we already know? The quest for answers continues, and with each step, our understanding of the universe grows deeper. Black holes, particularly supermassive ones, play a central role in shaping the structure and evolution of galaxies. These enigmatic entities, hidden deep within the cores of many galaxies, profoundly influence the very morphology of their host galaxies. Research shows a direct correlation between the size of a galaxy's bulge and the mass of the supermassive black hole residing at its center. Larger galactic bulges tend to be found in galaxies harboring more massive black holes, suggesting a symbiotic relationship, one where black holes and galaxies co-evolve over billions of years. This relationship is a testament to how gravitational forces and the exchange of energy between these dark giants and their surroundings mold the galactic environment, shaping the development of entire galaxies over cosmic timescales. The presence of supermassive black holes often leads to a host of intriguing phenomena. One such occurrence is the creation of new star clusters, which can be triggered by the immense gravitational forces exerted by these black holes. Additionally, the paths of stars within the galaxy may be altered, leading to drastic shifts in their orbits as they respond to the tidal forces from the black hole. Gravitational waves are incredibly faint by the time they reach Earth, making it necessary to use highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. This observatory uses laser beams to measure minute changes in distance caused by passing waves, detecting distortions in space-time on an incredibly small scale. The difficulty in detecting gravitational waves is compounded by their complexity. As they pass through space, these waves stretch and compress space-time, affecting distances at a subatomic level. This means that detection devices must maintain extraordinarily high precision to detect these minuscule distortions. Furthermore, the sources of gravitational waves vary greatly, producing signals with differing frequencies and amplitudes. To make sense of the data, scientists rely on sophisticated algorithms and data analysis techniques, which help to decipher the complex information embedded in the signals. What makes the study of gravitational waves so compelling is the fact that they provide a completely new way of observing the universe, one that differs from traditional electromagnetic waves, which have been studied for centuries. Gravitational waves were first predicted by Albert Einstein in the early 20th century, but it wasn't until recently that we developed the technology to detect them. As a relatively new field of study, much of the underlying physics of gravitational waves remains unexplored, and there is still much to learn about how these waves propagate, interact with matter, and reveal the nature of the universe itself. Each successful detection of a gravitational wave adds to our growing body of knowledge, shedding light on phenomena like the formation of black holes, the behavior of neutron stars, and the very nature of gravity. As scientists continue to refine their detection techniques, they open windows into moments of cosmic history that were previously invisible to us, allowing us to peer into the deepest, most mysterious regions of space. Quasars, or quasi-stellar objects, serve as incredibly bright beacons that offer a window into the early universe. Powered by supermassive black holes at the centers of distant galaxies, these objects are among the most luminous in the cosmos. As matter spirals into the black hole, it heats up to extreme temperatures and emits vast amounts of energy, often outshining entire galaxies. This intense brightness allows astronomers to study quasars that originated billions of years ago, providing a glimpse into the universe's infancy when galaxies and stars were still in the process of forming. By studying quasars, scientists gain valuable insights into the early stages of galaxy formation and evolution. The light emitted by these distant objects carries vital information about the composition of the universe at that time, including the presence of heavy elements. Observing the light from quasars enables astronomers to trace the enrichment of intergalactic gas with materials forged in the hearts of stars, offering a deeper understanding of how stars and galaxies evolved over time. This, in turn, reveals the intricate relationship between black holes and their host galaxies, further enriching our understanding of the cosmic processes that shape the universe. As researchers continue to explore the cosmos, the study of black holes, dark matter, dark energy, gravitational waves, and quasars will undoubtedly reveal new and surprising facets of the universe. Each discovery brings us closer to understanding the forces that govern the cosmos and the deep interconnections that bind the fabric of reality itself. Quasars, often considered cosmic beacons, act as natural telescopes that reveal the hidden wonders of the universe. These extraordinary objects emit light so powerful that, as it travels across vast expanses of space, it provides a glimpse into the universe's intricate makeup. Along the way, the light interacts with clouds of gas and the complex structures of the cosmos, offering scientists a unique opportunity to study the properties of the universe at different stages of its evolution. As this light makes its journey, it helps unravel critical aspects of the universe's expansion and the distribution of dark matter. These elements play a fundamental role in shaping the large-scale structure of the cosmos. Through the study of quasars, scientists are able to peer into the very fabric of the universe's history, particularly its early stages. Quasars are instrumental in understanding the era of reionization, a time when the universe underwent a dramatic transformation, shifting from a murky, opaque state to a transparent one, illuminated by the first stars. By examining these distant phenomena, scientists are gaining insights into the origins of the universe, its ongoing evolution, and the intricate web of interactions that shape the cosmos. Turning to another celestial puzzle, exoplanets, planets that orbit stars beyond our solar system, offer a tantalizing glimpse into the possibilities of life beyond Earth. The sheer variety in the conditions of these distant worlds presents both a challenge and an opportunity for researchers. Some exoplanets belong to a category known as hot Jupiters, gas giants that orbit perilously close to their parent stars. These planets are subjected to extreme heat and pressure, creating environments that seem inhospitable to life as we know it. But it's not just the extreme heat that captures scientists' attention. Exoplanets also exhibit a stunning range of atmospheric conditions. Some have thick, toxic atmospheres composed of hazardous gases like sulfuric acid, while others may lack an atmosphere entirely. The density and composition of an exoplanet's atmosphere play crucial roles in regulating its surface conditions, including temperature and pressure. These variations prompt vital questions about the adaptability of life. Could life, in some form, survive in these extreme environments? And if so, how might it differ from life on Earth? What forms could it take, and what kinds of chemical processes would it rely upon? Among the many intriguing exoplanet types are water worlds, planets entirely covered by vast, deep oceans. These alien oceans present a strikingly different environment from Earth's land and water balance. Such conditions raise questions about how life could develop on a planet without land masses, or how chemical processes necessary for life could unfold in an entirely aquatic environment. Even when exoplanets are found in the habitable zone of their star, where conditions might seem right for liquid water to exist, the potential for life remains uncertain. Stellar radiation, the presence of magnetic fields, and geological activity can all drastically alter a planet's ability to support life. With each new discovery, scientists are forced to rethink traditional definitions of habitability. This expanding understanding is opening up new discussions about what life might look like across the universe and what forms it could take on planets far beyond our reach. Weather patterns on gas giants like Jupiter and Saturn present a striking contrast to those on terrestrial planets such as Earth and Mars. Gas giants are composed predominantly of hydrogen and helium, and their thick atmospheres can extend thousands of kilometers deep into space. This unique composition leads to powerful, long-lasting storm systems. For example, Jupiter's Great Red Spot, an enormous storm that has been raging for over 300 years, is so vast that it could easily engulf the entire Earth. In contrast, terrestrial planets like Earth and Mars have solid surfaces and much thinner atmospheres. This limits the scale and duration of their storms. Earth, for instance, experiences weather phenomena driven by its oceans and seasonal changes, such as hurricanes and thunderstorms, which typically last from a few days to several weeks. These weather patterns are heavily influenced by factors such as land masses, temperature variations, and fluctuations in atmospheric pressure. Gas giants, with their unique atmospheric characteristics, also feature fascinating wind patterns. Jupiter, for example, has supersonic winds that can reach speeds of around 400 miles per hour. These winds, along with the complex atmospheric bands that circulate within these planets, create massive storms and turbulence. The absence of a solid surface means that these storms can interact and evolve over vast distances. While terrestrial planets experience localized weather influenced by geography, gas giants present extreme weather phenomena driven by immense atmospheric forces. The scale and intensity of these storms offer a stunning view into the dynamic nature of our solar system and highlight how different planetary environments shape the weather in truly remarkable ways. Venus, often dubbed Earth's twin due to its similar size and proximity to the Sun, holds a host of mysteries that extend far beyond its searing, inhospitable surface. Enveloped in a thick, toxic atmosphere dominated by carbon dioxide, Venus experiences a runaway greenhouse effect. The sulfuric acid clouds that cloak the planet trap heat, causing surface temperatures to soar to around 800 degrees Fahrenheit, making it the hottest planet in the solar system. This extreme heat raises profound questions about the potential for life on Venus, particularly in its distant past, when conditions might have been far milder. The exploration of Venus has revealed geological features that suggest the planet may have once had a much more temperate climate. Ancient riverbeds and mountainous formations indicate that liquid water may have once flowed on its surface. Scientists speculate that billions of years ago, Venus might have been a much more hospitable environment, possibly capable of supporting microbial life. Unraveling the reasons behind the planet's dramatic transformation into the hellish world we see today is one of the most significant challenges in planetary science. Further complicating the search for answers is the detection of phosphine gas in Venus's upper atmosphere. On Earth, phosphine is primarily produced by microbial life, sparking debates over whether life could still exist in the planet's clouds, where conditions are less extreme. Could this gas be a sign of living organisms in the clouds of Venus, possibly in forms we have not yet imagined? The search for life beyond Earth has taken on an exciting new dimension with Venus as a central player, continuing to inspire scientific curiosity and the quest to understand the origins of life in our solar system and beyond. However, this observation remains deeply contentious, sparking ongoing debates within the scientific community about its origins. The controversy hinges on whether phosphine, a compound detected in Venus's atmosphere, could be generated by non-biological processes, or if its presence truly points to the existence of life. As robotic missions continue their exploration of Venus, revealing secrets about its surface and atmospheric dynamics, the possibility of uncovering evidence of past or even present microbial life on the planet keeps drawing significant attention. Each new discovery not only enhances our understanding of Venus, but also broadens our perception of what life could potentially look like, especially in environments once thought to be completely inhospitable. The allure of Venus lies in the mysteries it holds. With every new insight, the potential to expand our knowledge of planetary science grows alongside a deeper understanding of life's adaptability in even the most extreme conditions. The planet's hostile surface, with its crushing pressures and intense heat, seems like an unlikely home for life, yet Venus continues to challenge our assumptions. The discovery of phosphine, a gas that on Earth is mostly associated with biological activity, only adds fuel to the fire of debate. Is this a sign of life, or can it be explained by other unknown chemical processes? This ongoing exploration of Venus ties into the broader search for life beyond Earth. Across the cosmos, scientists are on a quest to understand how life might exist in environments very different from our own. The exploration of distant planets, often located light years away, has become a thrilling chapter in the ongoing story of humanity's search for extraterrestrial life. A variety of cutting-edge techniques and technologies play crucial roles in unraveling these cosmic mysteries. One of the primary tools used in this exploration is the telescope, both ground-based and space-based. These advanced instruments allow scientists to capture light from distant stars and planets, enabling them to analyze the characteristics of these celestial bodies. The light that reaches Earth from stars and planets contains vital information about their composition, temperature, and even their potential for supporting life. This data is invaluable in our quest to understand distant worlds. Among the most significant discoveries in recent years has been the detection of exoplanets, planets that exist outside our solar system. One of the most effective methods for identifying these exoplanets is the transit method. This technique involves closely monitoring the brightness of a star, looking for periodic dips in light. When an exoplanet passes in front of its host star, it temporarily blocks some of the star's light, creating a detectable dip. By measuring how much light is blocked and the duration of the transit, scientists can estimate the size of the planet, as well as its distance from its star, providing essential information about its orbit. These insights help determine whether a planet might be in the habitable zone, the region around a star where conditions might be right for liquid water to exist. Another key observational technique is the radial velocity method. This method focuses on detecting the subtle wobble of a star caused by the gravitational pull of orbiting planets. As a planet orbits its star, it exerts gravitational force that causes the star to shift slightly in position. By measuring changes in the star's light spectrum, specifically shifts in wavelengths caused by the Doppler effect, scientists can gather data about the planet's mass and orbit. This provides additional clues to the planet's potential habitability, as well as its overall characteristics. Astrobiologists are also making significant strides in analyzing the atmospheres of distant planets using a technique called spectroscopy. When the light from a star passes through a planet's atmosphere, different gases in the atmosphere absorb specific wavelengths of light. These absorption patterns create a unique signature that can be decoded to determine the atmospheric composition of the planet. Crucially, this method can also identify gases that might serve as potential indicators of life, such as oxygen, methane, or even more subtle biomarkers. These advanced methods rely on cutting-edge technology and international collaboration. Together, they represent humanity's relentless pursuit of understanding the universe and the possibility of life beyond Earth. As our tools and techniques continue to improve, we move ever closer to uncovering the answers to some of the most profound questions in science. Meanwhile, the discovery of water on Mars has marked a groundbreaking achievement in the search for life beyond Earth. Water is essential for all known forms of life, and its detection on Mars raises crucial questions. Could life have ever existed there, or might it still exist in some form today? Over the years, scientists have detected water on Mars in a variety of forms, from ice at the planet's polar caps to briny liquid water that flows in certain craters. These findings suggest that Mars still possesses the vital ingredient for life, dramatically altering our understanding of the planet. Once thought to be a dry, barren world, evidence now indicates that ancient Mars may have had a much more Earth-like environment in its past. Rivers, lakes, and possibly even oceans may have once covered the surface, creating an environment where life could have flourished. If microbial life did exist on Mars in its ancient past, the study of these remains could reveal valuable insights into the conditions necessary for life to emerge. Such knowledge could also inform our search for life elsewhere in the universe, helping us understand what environments are most conducive to life. The discovery of water on Mars is not just a scientific curiosity. It has practical implications for future space exploration. Any future human missions to Mars will need to utilize local resources to sustain life, and water is one of the most critical resources for astronauts. If accessible water sources can be confirmed, it could significantly ease the challenges of prolonged stays on Mars, reducing reliance on costly resupply missions from Earth. For the future of human exploration and settlement on Mars, the discovery of water offers a promising pathway toward making human life on the red planet a reality. These developments represent only the beginning of a new chapter in humanity's exploration of the universe, one that is full of potential discoveries and the promise of understanding more about life in the cosmos. As we continue to push the boundaries of our knowledge, each new revelation brings us closer to answering the most fundamental question of all: are we alone in the universe? The search for water on Mars is not just a quest to find a vital resource for potential human colonization. It is deeply connected to our broader scientific efforts to understand the evolution of planets and the dynamics of climate change. Investigating how water has cycled on Mars offers valuable insights into similar processes on Earth and across the universe. This understanding enhances not only our comprehension of Mars itself, but also helps us better grasp the complex systems at play on our own planet and others, shedding light on the shared forces that govern the cosmos. Among the many groundbreaking tools used in space exploration, the Hubble Space Telescope stands as one of the most significant. Since its launch in 1990, this telescope has transformed our knowledge of the universe, providing unprecedented glimpses into the depths of space. One of Hubble's most striking discoveries is the revelation that the universe is not simply expanding, but doing so at an accelerating pace. By measuring the light emitted by distant supernovae, scientists were able to detect a mysterious force, now known as dark energy, that appears to be driving this acceleration. This finding has caused a profound shift in cosmological theories, raising more questions about the nature and composition of the universe than it answers. Hubble's discoveries don't stop there. It has also deepened our understanding of galaxy formation and evolution, revealing that galaxies are far more diverse than astronomers once imagined. Through the analysis of various galactic shapes, sizes, and colors, Hubble has uncovered a complex range of structures scattered across space. One particularly striking observation came from the galaxy cluster AEL 370, where Hubble captured arcs of light that were produced by gravitational lensing. This phenomenon, in which the gravity of massive objects bends light from behind them, allowed astronomers to observe far-off objects that were otherwise hidden from view. These observations not only demonstrate Hubble's capability, but also provide valuable clues about the nature of gravity and how it operates on a cosmic scale. In addition to investigating distant galaxies, the Hubble Space Telescope has captured stunning images of exoplanets, providing critical data about their atmospheres and compositions. One of its most exciting discoveries was the detection of water vapor in the atmosphere of an exoplanet located several hundred light-years away. This breakthrough suggests that the conditions necessary for life may exist beyond our solar system. The discovery has fueled optimism in the search for extraterrestrial life, showing that the possibility of finding habitable environments on other planets is far from science fiction. Moreover, Hubble has enriched our understanding of the life cycles of stars. The telescope has documented various nebulae, vast clouds of gas and dust that serve as the birthplaces of stars, capturing the stunning processes of star formation and supernova explosions. These detailed images allow scientists to track the evolution of stars from their birth to their explosive deaths, providing a comprehensive view of how elements are formed inside stars and then scattered across the universe. This material ultimately contributes to the complex structures that form galaxies and may even play a role in supporting life as we know it. Another major area of research is the study of cosmic rays, high-energy particles that originate from violent astronomical events like supernovae. These particles travel through space and sometimes collide with Earth's atmosphere, creating showers of secondary particles that can be detected by instruments both on the ground and in space. These cosmic ray showers offer a unique window into the fundamental processes of astrophysics and help scientists study the nature of far-off cosmic phenomena. By analyzing the energy and composition of these particles, researchers can uncover information about the composition of the universe itself, including the distribution of elements and the presence of exotic particles. This knowledge is vital for developing theories about the evolution of galaxies and the interstellar medium. Furthermore, cosmic rays contribute significantly to research in particle physics. When these high-energy particles collide with atoms in our atmosphere, they produce a cascade of secondary particles that can be studied to address fundamental questions about matter and energy. This intersection between astrophysics and particle physics has led to the development of advanced technologies and methods that further enhance our understanding of the universe at its most basic level. At the same time, cosmic rays raise intriguing questions about their potential effects on life here on Earth. While the Earth's atmosphere offers significant protection from these high-energy particles, some can still penetrate the surface. This phenomenon has important implications for both modern aviation and the potential for human space travel. Understanding the extent of cosmic radiation exposure is critical, not just for protecting astronauts on future missions to Mars, but also for exploring the broader implications of cosmic radiation on life on Earth. Another fascinating aspect of space exploration involves rogue planets, celestial bodies that do not orbit any star and instead drift through the vast emptiness of space. These planets, often described as the wandering nomads of the universe, come in a wide variety of sizes, compositions, and temperatures. Some may resemble gas giants like Jupiter, while others could be more similar to Earth with rocky surfaces. What makes them so intriguing is their ability to survive in the cold, dark void of space, far removed from the warmth of any nearby star. Their existence challenges our understanding of planetary formation and stability, as they appear to defy the conditions under which most planets are believed to form. There are several theories about how rogue planets come into being, and some may start their lives within a solar system, only to be ejected due to gravitational interactions with larger bodies or competing planets. Others may form in the protoplanetary disks surrounding young stars, but instead of settling into an orbit, they may escape the gravitational pull of their star, becoming rogue by chance. This phenomenon highlights the unpredictable and dynamic nature of planetary systems, underscoring the complexity of the forces at work in the universe. Rogue planets are not confined to a specific region of space. Some roam within our own Milky Way galaxy, and estimates suggest that there could be billions of such planets in our cosmic neighborhood. Some scientists have even speculated that rogue planets might exist in distant regions like the Oort cloud, a theoretical cloud of icy bodies located far beyond the orbit of Neptune. If true, this would suggest that our solar system itself may harbor these elusive wanderers, adding another layer of mystery to the vast expanse of space. Rogue planets, those mysterious wanderers of the cosmos, hold a captivating allure for astronomers and space enthusiasts alike. Drifting untethered through the vast emptiness of space, far beyond the gravitational grip of any star, they defy the conventional understanding of planetary formation and behavior. These planets, whose paths take them between galaxies, have the power to transform our perception of the universe's structure. But despite their potential to rewrite the narrative of planetary existence, their elusive nature presents a formidable challenge. Detecting rogue planets is not a straightforward task. Instead of observing them directly, astronomers often must rely on indirect methods that exploit their subtle influences on nearby celestial bodies. One such technique involves examining the gravitational effects that rogue planets exert on the orbits of nearby stars or cosmic objects. These interactions, while faint, offer the only clues to the presence of these rogue wanderers. Another method focuses on the thermal emissions of rogue planets, faint, distant glimmers of heat that might reveal their existence. Despite these challenges, the pursuit of rogue planets continues to be a significant focus in astrophysical research. By studying these free-floating worlds, scientists not only gain insights into the mechanics of planetary formation, but also unlock profound questions about the possibility of life in these isolated, starless realms. As our exploration of the cosmos deepens, these enigmatic planets will likely remain at the forefront of the conversation, constantly pushing the boundaries of what we know about the galaxy and the many mysteries it holds. In a more familiar corner of the universe, natural satellites, commonly known as moons, play a vital role in shaping the behavior of their host planets. Their influence extends across a range of processes, from tidal forces to geological activity, and their interactions with the planets they orbit often have lasting and profound consequences. Perhaps one of the most immediately noticeable effects of a moon is its gravitational pull, which drives the rise and fall of ocean tides on Earth. This interaction between Earth and its moon is responsible for the predictable patterns of tides that we observe on our planet. These tidal forces are not just an oceanic phenomenon. They ripple through marine ecosystems and even coastal environments, influencing the distribution of nutrients and the migration patterns of marine life. But the influence of moons extends far beyond the oceans. Moons can also have a stabilizing effect on their host planets, especially when it comes to axial tilt. Earth's axial tilt, which is responsible for our seasonal changes, is kept remarkably stable thanks to the gravitational forces exerted by our moon. Without this stabilizing influence, Earth's axis could wobble unpredictably, leading to extreme climatic fluctuations. Such instability could drastically alter the conditions necessary for life to thrive. In this way, moons don't merely accompany planets. They are active players in maintaining the delicate balance that allows ecosystems to flourish. Moreover, moons can also act as catalysts for geological processes. Take Jupiter's moon Io, for example. Io is the most geologically active body in the entire solar system, thanks in large part to the tidal forces exerted by Jupiter. These forces create intense friction inside Io, leading to volcanic eruptions that constantly reshape the moon's surface. Similarly, on other planets, the interaction between a planet and its moons can lead to geological changes that shape the planet's surface over time. Whether these forces result in the formation of mountains, valleys, or volcanic activity, moons have the power to drive a planet's geological evolution. Even more intriguing is the potential role moons play in shaping the atmospheres of their host planets. As moons interact with the solar wind, the stream of charged particles emitted by the sun, they can influence the retention or loss of atmospheric particles. This process could play a critical role in a planet's atmospheric evolution over billions of years. The loss or preservation of a planet's atmosphere, in turn, directly impacts its habitability. A moon's gravitational pull, combined with its relationship with the solar wind, could determine whether a planet retains the conditions necessary for sustaining life. The interconnectedness between planets and their moons is a striking example of how celestial bodies influence one another across the cosmos. It's a reminder that the fates of these worlds are often entwined in ways that can have far-reaching consequences. While the Earth-Moon system has been the subject of extensive study since the Apollo missions, many of the moon's features remain shrouded in mystery. Through telescopes and spacecraft, scientists have observed various geological formations, but much of the moon's landscape still awaits detailed exploration. One particularly intriguing area of the moon that has captivated researchers is the far side. Unlike the near side, which constantly faces Earth, the far side presents a completely different geological landscape, including the South Pole Aitken Basin, the largest and oldest impact basin in the solar system. This massive depression offers a glimpse into the moon's violent history and could hold valuable clues about the formation of not just the moon, but the entire solar system. But the far side is just the beginning. Beneath the moon's surface, a network of lunar lava tubes awaits exploration. These tunnels, formed by flowing molten rock, could reveal much about the moon's volcanic past, providing insights into the internal workings of this celestial body. Some of these lava tubes are large enough to shelter entire bases, offering potential refuges for astronauts in the future. These subterranean shelters could protect occupants from the harsh radiation and extreme temperatures found on the moon's surface, making them vital to the long-term sustainability of lunar exploration. Another exciting avenue of research involves the presence of water ice in the permanently shadowed craters at the lunar poles. Radar observations have hinted at the existence of ice, but its quantity and accessibility remain uncertain. If confirmed, this water could play a crucial role in supporting future lunar habitats, providing essential resources for human life on the moon. Furthermore, water ice could serve as a vital fuel source for missions beyond the moon, potentially fueling spacecraft heading deeper into the solar system or even interstellar space. As research and exploration of the moon intensify, new missions from both government space agencies and private companies are poised to unlock new secrets. These endeavors promise to push the boundaries of our knowledge, offering discoveries that could reshape our understanding of the moon's past and its role in humanity's future in space. The moon, once thought to be a desolate rock in the sky, is now seen as a treasure trove of possibilities, one that continues to inspire and captivate the imaginations of scientists, engineers, and dreamers alike. The moon's exosphere, though incredibly thin, is a fascinating region that contains trace gases and a variety of unique elements. While it may seem almost inconsequential due to its rarity, analyzing these gases offers scientists rare clues about the moon's formation and its evolutionary history. With continued exploration, including future landings and sample returns, we stand on the brink of uncovering more about this enigmatic celestial body. These discoveries promise to deepen our understanding of Earth's closest neighbor, revealing that even within our own backyard, there is still so much to learn. Meanwhile, the Andromeda Galaxy, also known as M31, captivates astronomers and space enthusiasts alike. Its proximity and sheer scale make it an object of intense fascination. Located approximately 2.5 million light-years from our Milky Way, Andromeda is the nearest spiral galaxy to our own. This closeness allows astronomers to study its structure, star formation, and dynamics in extraordinary detail, offering unprecedented insights into the processes that govern the evolution of galaxies. One of the most striking aspects of Andromeda is its immense size. With a diameter that spans over 200,000 light-years, it is more than twice the size of our Milky Way galaxy. Within this vast expanse, Andromeda hosts around 1 trillion stars. This immense stellar population offers a unique opportunity to observe a wide variety of star types, including massive, short-lived stars that burn intensely quickly, as well as older, cooler stars that offer glimpses into the different stages of galactic evolution. Astrophysicists are particularly drawn to Andromeda because of its significance in understanding the future of the Milky Way. Predictions suggest that the two galaxies are on a collision course, with a projected collision set to occur in approximately 4 billion years. When these two massive galaxies collide, the results will be profound, triggering new star formation as the gravitational forces from the merger compress vast clouds of gas. The ultimate outcome will likely be the creation of a new, larger elliptical galaxy. Thus, the study of Andromeda holds critical value in helping scientists predict and understand the future of galactic interactions and their far-reaching consequences. Beyond its sheer size and future collision course, Andromeda's extensive collection of satellite galaxies adds another layer of intrigue. These smaller galaxies orbit around the larger Andromeda Galaxy, forming a complex gravitational ecosystem that plays a crucial role in advancing our understanding of dark matter. Dark matter, which constitutes a significant portion of the universe's mass but remains largely invisible and elusive, can be studied through the interactions between Andromeda and its satellites. These interactions offer a rare opportunity to explore the hidden forces that govern the structure and behavior of the cosmos, providing essential data for advancing astrophysical research. The dynamics of galaxy collisions, including the potential merger between the Milky Way and Andromeda, are anything but straightforward. When two galaxies collide, the process is highly complex, unfolding over millions of years. Initially, the galaxies pass through each other without their stars directly colliding due to the vast distances between them. However, the gravitational forces at play begin to distort the galaxies' shapes. These interactions give rise to tidal tails, long streams of stars and gas that stretch out into space. As the collision progresses, the galaxies move ever closer, eventually merging into a singular, larger galaxy. During this process, bursts of star formation, called starbursts, can occur. These bursts are triggered when clouds of gas collide and compress, igniting new stars at a rate far exceeding the typical star formation observed in galaxies that are not undergoing such collisions. As these new stars light up, they illuminate the surrounding gas, creating a spectacular visual display that alters the very fabric of the galaxies involved. The aftermath of such a collision typically results in the formation of elliptical galaxies, which are characterized by their smooth, featureless appearance, in stark contrast to the spiral arms of galaxies like the Milky Way and Andromeda. The study of these evolving galaxies offers invaluable insights into the life cycles of galaxies and their ultimate fate. It also sheds light on the role of dark matter, which plays a pivotal role in the gravitational interactions that drive these mergers. In fact, many of the galaxies we observe today have likely undergone one or more merger events throughout their history. These cosmic collisions have shaped the unique characteristics of each galaxy, influencing their structure, star populations, and overall dynamics. Colliding galaxies also present a host of fascinating mysteries. For example, the fate of individual stars within these galaxies is unpredictable. Some stars may be flung outward into the vastness of intergalactic space, while others may become permanently integrated into the newly formed galaxy, finding their place in a completely different cosmic environment. These galactic mergers not only serve as captivating subjects for scientific study, but also offer a profound understanding of the complex and dynamic nature of the universe. As we continue to explore the far reaches of space, we are continually reminded that the universe, in all its complexity, remains a place of constant change and discovery. Each new piece of knowledge brings us closer to understanding the processes that shape galaxies, stars, and the very fabric of space-time itself. The role of supermassive black holes at the centers of galaxies raises intriguing questions, opening up a world of possibilities that could redefine our understanding of the cosmos. As galaxies merge, their supermassive black holes, which lie at their cores, move closer to each other, potentially resulting in awe-inspiring interactions. These cosmic events challenge our perceptions of galactic evolution and hint at deeper, more complex relationships between galaxies and the universe itself, relationships that we have yet to fully uncover. Barred spiral galaxies in particular possess unique characteristics that set them apart from other galactic structures. One of the most defining features of these galaxies is their central bar-shaped structure, a formation that extends across the nucleus and stretches out toward the spiral arms. This bar acts as a gravitational anchor, playing a critical role in the motion of stars and gas within the galaxy. As a result, the spiral arms of barred spiral galaxies are often more tightly wound than those of their non-barred counterparts, offering a striking visual difference. The formation of these bars is believed to be a consequence of dynamic forces within the galaxy. Over time, gravitational interactions and the rotation of the galaxy can instigate instabilities, which in turn lead to the creation of these elongated formations. The central bar plays a vital role in funneling gas toward the core of the galaxy, sparking an increase in star formation activity in this region. As a result, barred spiral galaxies tend to exhibit a higher rate of star formation than their non-barred counterparts, further enriching the complex interplay of forces within the galaxy. Another fascinating aspect of barred spiral galaxies is the diversity of their structures. These galaxies can vary greatly in size and in the brightness of their spiral arms. Some barred spirals feature an extremely prominent bar, while others present more subtle variations. This range of forms offers astronomers an invaluable opportunity to study the dynamics of galaxies, providing essential insights into how cosmic forces shape their development over time. Barred spiral galaxies are also crucial to understanding the evolution of galactic ecosystems. The bars themselves facilitate the redistribution of matter and energy, triggering various star formation events and influencing the galaxy's overall evolution across billions of years. This process highlights the dynamic nature of the universe, demonstrating that galaxies are not static, but are instead in a constant state of flux. Starburst galaxies offer yet another captivating window into the complex nature of galactic evolution. These galaxies are characterized by an exceptionally high rate of star formation. While typical galaxies create stars at a steady pace, starburst galaxies can form new stars at rates several times higher than in more typical galactic environments. This intense rate of star formation leads to the birth of thousands of stars every year, often packed into dense regions that emit brilliant, vibrant light. The explosive activity within starburst galaxies is largely driven by galactic interactions. When two or more galaxies collide or come close to one another, their gravitational forces disrupt the gas and dust within each galaxy, igniting a surge of star formation. This phenomenon is so intense that it often leads to the creation of massive stars that burn quickly and intensely, only to explode as supernovae, further shaping their surroundings. Along with galactic collisions, the abundance of gas is also a critical factor in the formation of starburst galaxies. Dense clouds of gas can collapse under their own gravity, giving rise to millions of new stars in the process. Starburst events can span anywhere from a few million to several hundred million years. During this period, the galaxy undergoes significant transformation, becoming irregular and chaotic in appearance when compared to the more orderly, disk-like structures seen in typical galaxies. As these starbursts progress, newly formed stars, especially massive ones, contribute to a feedback process that can blow out gas and dust from the galaxy. This outflow can both alter the galaxy's structure and influence its evolution, enriching the surrounding intergalactic medium with heavier elements. However, as the starburst event consumes the available gas, it eventually leads to a slowing of the star formation process, quenching the galaxy's ability to create new stars. The dynamic life cycle of starburst galaxies provides astronomers with invaluable insights into the birth and evolution of galaxies throughout the universe. These extreme environments offer a unique perspective on the forces that govern galactic development and the birth of stars. At the heart of many galaxies, including our own Milky Way, reside supermassive black holes. These enigmatic objects, which can weigh millions to billions of times more than our Sun, exert a powerful influence on their host galaxies. The presence of supermassive black holes shapes the formation and evolution of galaxies in profound ways. These black holes likely formed through the merging of smaller black holes and the accumulation of gas and stars over cosmic time. As galaxies evolve, the supermassive black holes at their centers continue to grow, and their gravitational pull profoundly impacts the motion of stars and gas in the surrounding region. This gravitational influence creates a dynamic environment within the galaxy, affecting star formation and altering the galaxy's overall structure. Depending on the interaction between the black hole and its surrounding environment, star formation may be either enhanced or inhibited, leading to further changes in the galaxy's development. In essence, supermassive black holes are not just passive observers of galactic evolution. They are active participants in shaping the destiny of the galaxies that surround them. Their gravitational influence serves as a powerful force that drives the motion of stars, the formation of new stars, and the overall cosmic evolution of the galaxies themselves. As our understanding of these black holes deepens, we gain more insight into the complex and intricate relationships that govern the evolution of galaxies on the largest scales. When matter plunges into a supermassive black hole, it triggers an extraordinary process, one that generates immense energy. The black hole's powerful gravitational forces propel jets of high-energy radiation and particles into the surrounding space. This event creates a cascade of feedback effects, influencing not only the immediate environment, but also the entire galaxy in which the black hole resides. Gas is expelled from the galaxy, and its temperature soars, leading to an intricate regulation of star formation. This feedback loop plays a critical role in shaping the galaxy's evolution, with the activity of the supermassive black hole affecting the pace and extent of star birth. The relationship between a galaxy and its supermassive black hole is often described as a co-evolutionary process where the growth and development of one influence the other. As galaxies evolve, so too do the black holes at their centers, with these two cosmic entities experiencing a symbiotic relationship. The black hole, in a sense, holds the galaxy's fate in its gravitational grip, while the galaxy provides the essential matter required for the black hole's growth. This delicate balance has profound implications for the long-term fate of galaxies, dictating not only their star formation rates, but also their overall dynamics and structure. Understanding this intricate dance between galaxies and their supermassive black holes is one of the most significant challenges in modern cosmology, shedding light on the complex and interconnected nature of the universe. Meanwhile, theories of cosmic inflation offer a fascinating lens through which to view the uniformity of the universe. This uniformity refers to the way matter, energy, and cosmic radiation, specifically the cosmic microwave background radiation, are distributed across vast stretches of space. Despite the universe's immense size, these quantities are astonishingly consistent, suggesting that distant regions of space separated by billions of light years share remarkably similar conditions. The key idea behind cosmic inflation is that, in the earliest moments after the Big Bang, the universe experienced an extraordinarily rapid and exponential expansion. In an incredibly short time, the fabric of space-time stretched dramatically, causing regions that were once close together to be separated by vast distances. During this period of inflation, tiny quantum fluctuations, imperceptibly small irregularities in the fabric of space, were stretched to cosmic proportions, These fluctuations acted as the seeds from which galaxies and large-scale structures in the universe would later emerge. Because of inflation, regions that were once in close proximity became so far apart that they could never have interacted with one another, yet they share similar properties due to their common origins. This uniformity provides strong evidence for the inflationary theory, with the cosmic microwave background radiation acting as a crucial indicator. The radiation's near-perfect equilibrium across the sky suggests that the universe's expansion did not result in the chaotic distribution of energy and matter that one might expect over such enormous distances. Moreover, the inflationary model resolves several long-standing puzzles in cosmology, such as the flatness problem and the horizon problem. These issues posed significant questions about the uniformity of the universe. How, for example, could regions of the universe separated by such vast distances share the same temperature and density without any means of communication between them? The theory of inflation offers an answer. The rapid expansion in the early universe caused all regions to converge toward the same conditions, explaining the striking homogeneity we observe today. By addressing these fundamental questions, cosmic inflation not only strengthens our understanding of the universe's origins, but also illuminates the mechanisms that allowed for its grand-scale structure to emerge in such a uniform manner. Shifting our focus to a more speculative yet equally captivating concept, multiverse theories have opened the door to radical new possibilities about the nature of reality itself. The idea that our universe might be just one of many that coexist challenges the conventional view of a single, unique universe. Each universe within this vast multiverse could have its own set of physical laws and constants, leading to a bewildering array of possible realities. In this framework, the boundaries of possibility stretch beyond our imagination, suggesting that in some alternate universe, different versions of historical events have unfolded, or life forms have evolved along completely different paths. One of the most intriguing aspects of the multiverse hypothesis is the way it redefines probability. In a multiversal context, every possible outcome of every event could potentially occur somewhere in the vast expanse of parallel universes. This concept forces us to reconsider the very nature of what is possible, as even the most extraordinary or improbable events might happen in some corner of the multiverse. This idea brings forth an entirely new way of thinking about the concept of reality, where our universe represents just one of many potential outcomes, each with its own set of circumstances and possibilities. Moreover, the multiverse theory intersects in fascinating ways with the principles of quantum mechanics. For example, the many worlds interpretation of quantum mechanics suggests that each time a quantum event occurs, whether it's the decay of a particle or the position of an electron, the universe splits into multiple branches, each representing a different possible outcome. This interpretation has profound implications for our understanding of fate, free will, and the interconnectedness of all things. If every possible outcome exists in some reality, it fundamentally alters our perception of choice and chance, offering a new perspective on the nature of existence. Though still speculative, multiverse theories compel scientists and philosophers alike to expand their thinking and confront profound questions about the nature of existence. These theories challenge the very essence of reality, inviting us to consider the possibility that what we see and experience is only one version of a much larger, far more complex existence. As research continues into these ideas, the multiverse remains a compelling frontier in the study of the cosmos, urging us to rethink not only the structure of the universe, but the fundamental nature of reality itself. In a similarly profound realm of inquiry, recent advances in the study of antimatter have brought us closer to unraveling some of the universe's most fundamental mysteries. Antimatter, the elusive counterpart to ordinary matter, is made up of particles that have the same mass as their matter counterparts, but carry opposite charges. For example, while electrons carry a negative charge, their antimatter counterpart, the positron, has a positive charge. The study of antimatter raises some of the most intriguing and challenging questions in physics, particularly regarding the origins of the universe and the apparent imbalance between matter and antimatter. The Big Bang Theory posits that equal amounts of matter and antimatter should have been created during the universe's inception. However, observations show that the universe is overwhelmingly made of matter, with very little antimatter present today. This imbalance has puzzled scientists for decades, and understanding its origins could be key to unlocking some of the universe's deepest secrets. As researchers delve further into the properties of antimatter, they may uncover new insights that could reshape our understanding of the cosmos at its most fundamental level. However, observations in the field of cosmology have revealed an intriguing and persistent mystery: the striking dominance of matter over antimatter in the observable universe. This imbalance leads to a critical question: where did all the antimatter go? According to current understanding, the Big Bang should have produced equal amounts of both matter and antimatter. Yet, the universe appears to be overwhelmingly made up of matter, with antimatter nearly absent, raising one of the most profound puzzles in modern physics. This enigma has inspired scientists and researchers worldwide to embark on extensive experiments, particularly at particle accelerators, in a bid to uncover the secrets behind this asymmetry. These experiments are focused on exploring the properties of antimatter, with the aim of revealing any potential differences in its behavior compared to regular matter. The studies surrounding antimatter are not merely theoretical. They hold the potential to revolutionize our understanding of the cosmos. The key question driving much of this research is what could have caused this imbalance between matter and antimatter. Understanding the origin of this disparity might provide new insights into the evolution of the universe and could even lead to breakthroughs in the fundamental laws of physics. Moreover, these investigations have extended into the fascinating possibility that antimatter might harbor unique and powerful forms of energy. For instance, when matter and antimatter collide, they annihilate each other, releasing an enormous burst of energy in the process. This remarkable phenomenon, with its immense energy output, has inspired speculation about potential applications. Could antimatter one day be harnessed as an energy source, or could it be used in propulsion systems to power spacecraft, enabling interstellar travel? Though these ideas currently reside firmly in the realm of theoretical speculation, the scientific investigation into antimatter provides a fertile ground for imagining future technologies that could dramatically expand our capabilities in space exploration and beyond. One particularly intriguing area of research is the capture and study of antihydrogen, the simplest atom of antimatter. By studying antihydrogen, scientists hope to gain deeper insights into the properties of antimatter and determine whether it behaves differently from regular hydrogen. If it can be shown that antihydrogen exhibits distinct characteristics, it could lend significant support to theories attempting to explain the long-standing asymmetry between matter and antimatter. As these investigations unfold, they not only hold the promise of answering age-old questions, but also open up exciting new avenues for exploration in cosmology and physics, potentially transforming our understanding of the universe at its most fundamental level. One of the cornerstones of modern cosmology is the cosmic microwave background radiation, CMB, which serves as a crucial relic from the infancy of the universe. This faint and pervasive radiation, which fills the universe, acts as a snapshot of the cosmos just over 380,000 years after the Big Bang. During this early period, the universe had cooled sufficiently for protons and electrons to combine into hydrogen atoms, allowing photons, light particles, to travel freely through space. This event marked a significant transition, as the universe shifted from a hot, opaque state to a transparent and observable one, much like the clear cosmos we observe today. The cosmic microwave background is more than just a faint remnant of the past. It is an invaluable tool for scientists seeking to unlock the mysteries of the early universe. By analyzing the CMB, researchers can glean profound insights into the conditions that prevailed shortly after the Big Bang. One of the key pieces of information it provides is the distribution of matter in the early universe. These patterns are critical, as they offer clues about how galaxies and large-scale cosmic structures began to form. Even the tiniest fluctuations in the temperature of the CMB correspond to density variations in the early universe, painting a picture of the seeds of galaxies that would eventually come to dominate the cosmos. Moreover, the cosmic microwave background is indispensable in testing cosmological models. By studying its properties in detail, scientists can determine critical parameters of the universe, such as its age, its composition, and the rate at which it is expanding. Over the years, space missions like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory have gathered highly precise data, refining our understanding of elusive phenomena like dark energy and dark matter. The evidence provided by the CMB is a powerful endorsement of the Big Bang Theory, reinforcing the idea that the universe has evolved over billions of years from a hot, dense state to the vast and complex system we observe today. In this way, the CMB serves as a tangible connection to the early universe, allowing scientists to peer back in time and unravel the mysteries of cosmic history. The cosmic microwave background continues to be a focal point of cosmological research, pushing the boundaries of our knowledge and understanding of the universe. It prompts scientists to ask new questions and seek answers that may redefine our grasp of the cosmos. In addition to the CMB, there are other observable variables that play crucial roles in the quest to understand the origins of the universe. These variables include the distribution of galaxies, the abundance of light elements such as hydrogen and helium, and the various other phenomena that help piece together the cosmic puzzle. Each of these aspects provides vital data that inform theoretical models about the universe's birth and evolution. For example, the distribution of galaxies across vast cosmic distances reveals essential information about how the universe has evolved. By examining how galaxies are clustered together and the rate at which they are moving apart, scientists can infer the dynamics of cosmic expansion and the influence of gravity. This observational data supports the prevailing model of an expanding universe, which was first proposed by astronomer Edwin Hubble. Hubble's discovery that distant galaxies are moving away from us, causing the universe itself to grow larger over time, has become one of the foundational pillars of modern cosmology. In sum, these observable variables, whether the cosmic microwave background radiation, the distribution of galaxies, or the abundance of light elements, serve as the building blocks of our understanding of the universe. By carefully studying these phenomena, scientists continue to refine our models of the universe's origins, its evolution, and its ultimate fate. Each new discovery helps bring us closer to unraveling the deepest mysteries of the cosmos, illuminating the path toward a more complete understanding of the universe in which we live. The universe, vast and unfathomable, holds within it a wealth of clues about the moments that followed the Big Bang, clues that have the potential to rewrite our understanding of how it all began. Among the most significant of these clues are the light elements scattered throughout the cosmos. These elements, hydrogen, helium, and trace amounts of lithium, offer us a glimpse into the earliest moments of cosmic history. They tell a story of nucleosynthesis, a process that took place as the universe cooled after its violent birth. The patterns and ratios of these elements match remarkably well with the predictions made by Big Bang nucleosynthesis models, lending weight to the theories that aim to explain the origins of everything we see today. As scientists piece together these observable data points, a clearer picture of the universe's early days emerges, inviting us to ponder the very nature of existence itself. As this quest for understanding extends beyond our own solar system, we encounter fascinating and strange worlds. These exoplanets orbiting distant stars present conditions that challenge our preconceptions about what constitutes a habitable environment. Take, for example, WASP-72b, a gas giant located approximately 40 light-years from Earth. Its atmosphere is perpetually bloated, an effect of the blistering temperatures exceeding 1,000 degrees Celsius. Such extreme heat ensures that the planet's atmosphere is filled with metallic clouds, creating a world of constant, surreal firestorms. This raises a provocative question. Could life exist in such a searing environment, or would it be impossible to survive under such intense conditions? Another exoplanet, TRAPPIST-1d, presents an entirely different kind of enigma. Located in a system of 7 Earth-sized planets, this world resides within the so-called habitable zone, a region where temperatures might allow for liquid water. However, its atmosphere is thought to be so dense that it would generate immense surface pressures, creating an environment unlike anything we experience on Earth. With unpredictable weather systems and constant atmospheric turbulence, life here would have to adapt to challenges that seem foreign to us. This forces a rethink of what constitutes habitability, prompting scientists to expand the boundaries of their assumptions. Kelt 11b, a gas giant orbiting a star 500 light-years away, presents yet another compelling case for rethinking the potential for life in extreme environments. Its temperature is so high that the planet may host clouds made of molten glass. The fierce winds on this planet would create conditions so extreme that only the hardiest forms of life could endure. Such an environment challenges our traditional understanding of biology. Could life exist in forms we cannot even imagine, thriving under temperatures that melt metal and pressures that crush the human body? These extreme exoplanets are far more than curiosities. They are windows into the unknown. As scientists explore these alien worlds, they expand the parameters of what might be considered a habitable zone. The idea that life could exist in forms radically different from anything we've ever encountered forces us to reconsider not only the scope of life beyond Earth, but the very nature of life itself. As technology advances, the boundaries of astrobiology stretch ever further, making us ask, could life be thriving on worlds that are far harsher than we can conceive? The search for extraterrestrial intelligence, ETI, is undergoing a dramatic transformation. Once confined to the realms of speculation and science fiction, the search is now a serious scientific endeavor, propelled by advances in technology and new methodologies. Modern telescopes equipped with powerful sensors and unprecedented sensitivity allow us to study distant exoplanets with incredible precision. Instruments like the James Webb Space Telescope can peer into the atmospheres of these worlds, searching for signs of life in the form of chemical signatures. Substances like oxygen, methane, and carbon dioxide, often associated with biological activity on Earth, are among the key molecules being hunted for. Artificial intelligence is also playing a crucial role in this search. With machine learning algorithms, vast amounts of data gathered from distant planets can be analyzed at a speed and depth beyond human capability. These algorithms can sift through cosmic signals, detecting patterns that may elude even the most experienced astronomers. As a result, the chances of detecting artificial signals, potential indicators of extraterrestrial civilizations, are increasing. The ever-growing sophistication of signal processing techniques also helps to filter out cosmic noise, honing in on signals that could have genuine significance. Radio astronomy remains a cornerstone of the search for extraterrestrial life, and new projects like SETI, Search for Extraterrestrial Intelligence, are making significant strides. Advanced arrays of antennas allow researchers to scan the cosmos more efficiently, looking for artificial signals that stand out from the usual background radiation of the universe. By observing a broad range of frequencies simultaneously, astronomers increase the likelihood of detecting signals from advanced alien civilizations. Collaborative efforts, including international SETI initiatives, are pooling resources and expertise to enhance the search, ensuring that no stone is left unturned in the quest to find life beyond Earth. Additionally, the rise of citizen science has opened up new avenues for engagement. Projects that allow members of the public to analyze radio signals, images, and other data are providing an invaluable supplement to professional research efforts. These initiatives not only accelerate the search for extraterrestrial intelligence, but also inspire a shared sense of wonder and curiosity about the vast universe we inhabit. The growing convergence of cutting-edge technologies and collective human effort is transforming humanity's search for answers to one of the oldest questions we have. Are we alone in the universe? As we look to the stars, we are increasingly equipped with the tools and knowledge to find out. In addition to searching for signs of intelligent life, scientists are also scrutinizing the atmospheres of distant exoplanets for clues about their potential to support life. By analyzing the chemical composition of these atmospheres, researchers can deduce much about the planet's environment. Oxygen, methane, and carbon dioxide are particularly intriguing. On Earth, these gases exist in a delicate balance, and their presence together suggests the possibility of biological activity. For instance, oxygen is often a byproduct of photosynthesis, a process that is fundamental to life as we know it. However, the mere presence of oxygen is not enough to confirm life. When methane is found alongside oxygen, the situation becomes more compelling. These two gases, when found together, create a dynamic equilibrium that is difficult to sustain without some form of active biological process. On Earth, methane would break down rapidly in the presence of oxygen. So if both gases are detected in the atmosphere of an exoplanet, it suggests that some process, possibly biological, is keeping them in balance. The search for life beyond Earth is thus not just about detecting individual elements, but understanding the intricate interactions between them. The presence of certain molecules in the right combinations could be the key to unlocking the mystery of whether life exists elsewhere in the universe. The search for life beyond Earth hinges on our understanding of the atmospheres of distant planets and moons. One of the key components in this pursuit is water vapor. Water is widely regarded as essential for life as we know it. Its presence in a planet's atmosphere can significantly elevate its potential as a candidate for supporting life. Water, in its various forms, plays a critical role in facilitating the complex biochemical processes that sustain living organisms. Therefore, when scientists detect water vapor on distant worlds, it could indicate a planetary environment that may be conducive to biological activity. However, water alone is not enough to guarantee life. The specific conditions within a planet's atmosphere, including temperature, pressure, and the presence of clouds, are equally vital in shaping the climate and determining whether those conditions could support life. The balance of these factors creates a delicate equilibrium, one that can either foster or hinder the development of life. Understanding how these elements interact in distant environments allows scientists to assess their habitability and consider the broader implications for life beyond Earth. Each new discovery in this field offers fresh insights into the types of conditions that might support life, expanding our understanding of what is truly necessary for life to thrive in the cosmos. This pursuit of knowledge about alien atmospheres draws heavily on the lessons we've learned from studying Earth's own atmosphere. The Earth's atmosphere is an intricate system with a delicate balance between gases like nitrogen, oxygen, and carbon dioxide, which sustain life on this planet. Even slight fluctuations in the concentrations of these gases can trigger major environmental shifts, such as climate change. By studying Earth's atmosphere, scientists have gained valuable insights into the role that atmospheric composition plays in supporting life. These insights provide a critical framework for assessing the atmospheres of distant planets, allowing researchers to identify environments that might closely resemble our own. The balance of pressure and temperature in Earth's atmosphere is another crucial factor in determining its habitability. Earth's atmosphere shields us from harmful solar radiation, while also helping to regulate temperature and create a stable environment for life. When exploring other planets, scientists must consider how atmospheric pressure and temperature could affect the potential for life. Take Venus, for example. Its dense, toxic atmosphere and extreme surface temperatures present insurmountable challenges for any form of life. In contrast, Earth's milder conditions provide a more favorable environment. Understanding these dynamic atmospheric factors enables scientists to prioritize planets and moons where conditions may be more conducive to life, allowing them to focus their efforts on the most promising worlds. Another invaluable lesson Earth's atmosphere provides is the understanding of erosion and weathering, processes that shape a planet's surface. On Earth, the interplay of wind, rain, and temperature fluctuations has sculpted diverse landscapes and influenced climate patterns. By studying these processes here, scientists can extrapolate similar phenomena on other planets. For instance, the discovery of ancient river valleys or sediment deposits on Mars could offer vital clues about the planet's past climate and its potential to harbor life. These features could indicate that Mars, once a much warmer and wetter world, might have supported microbial life in its distant past. In turn, these lessons about Earth's atmosphere not only guide our search for habitable environments beyond our planet, but also help inform our understanding of climate change here at home. Studying alien worlds gives us a broader perspective on the interconnectedness of planetary atmospheres, shedding light on the delicate balance required to sustain life. Each new discovery about the atmospheric conditions of distant planets deepens our comprehension of the universe and strengthens our ability to protect the fragile environment we inhabit. The search for life beyond Earth is also driven by advanced technology and sophisticated scientific techniques. One of the most powerful tools in this search is spectroscopy. This technique involves analyzing the light that passes through or reflects off a planet's atmosphere. By studying the chemical fingerprints in this light, scientists can identify specific gases present in the atmosphere. Some gases, such as oxygen and methane, are closely associated with biological processes on Earth. When these gases are found together in significant quantities, they suggest the possibility of life. This is one of the most direct ways to identify potential biosignatures or signs of biological activity on distant worlds. Telescopes, particularly those positioned in space, play a crucial role in this exploration. The Hubble Space Telescope and the James Webb Space Telescope, for instance, are at the forefront of this groundbreaking research. These instruments can capture the light emitted or reflected by distant planets, offering valuable clues about their atmospheric composition. The James Webb Space Telescope, with its advanced infrared capabilities, can peer deep into the atmospheres of exoplanets, revealing details that were once beyond our reach. This capability allows scientists to examine the chemical makeup of distant worlds with unprecedented precision. In addition to atmospheric composition, the search for life often focuses on planets located in the habitable zone, the region around a star where conditions may allow liquid water to exist on the planet's surface. Liquid water is considered essential for life as we know it, making planets within the habitable zone prime targets for exploration. Scientists look for planets that share similar characteristics with Earth, such as size, temperature, and the presence of water. By honing in on these specific traits, researchers increase the likelihood of finding planets that could harbor life. As technology continues to advance, scientists are developing increasingly sophisticated models to better understand how life might exist under different environmental conditions. These models take into account not just the potential for liquid water, but also the unique conditions that might support life in forms we cannot yet imagine. By piecing together these various clues, researchers hope to unravel the mysteries of life beyond Earth, making groundbreaking discoveries about the nature of life in the universe. Meanwhile, on a grander cosmic scale, there are events in the universe that challenge our understanding of stellar evolution and the forces that shape the cosmos. One such phenomenon is the hypernova, an incredibly powerful stellar explosion that occurs under very specific conditions. Hypernova are among the most energetic events in the universe, often associated with the deaths of massive stars. These stars, which have masses more than 30 times that of our Sun, end their lives in a cataclysmic explosion known as a supernova. When the core of such a star collapses under the force of gravity, it can trigger a hypernova, releasing vast amounts of energy and creating heavy elements that are scattered throughout the universe. These cosmic events, while far from our daily lives, play a fundamental role in the evolution of galaxies and the creation of elements that are essential for life. Understanding these events not only sheds light on the death of stars, but also helps us understand the birth of the elements that make up the planets and life forms we study. As we continue to search for life beyond Earth, these stellar processes remind us of the profound interconnectedness of the universe and the complex forces that shape it. Through the study of distant atmospheres, the search for biosignatures, and the examination of stellar phenomena, scientists are expanding the frontiers of human knowledge. Every discovery, every breakthrough adds a new piece to the puzzle of life's existence in the cosmos. And in doing so, we are not just learning about the universe, we are learning about ourselves, our planet, and the fragile conditions that sustain life here on Earth. However, if the mass of the star's core is sufficiently great, it can lead to a truly catastrophic and breathtaking event, the hypernova. Unlike the more commonly observed supernova, which occurs when a star's core collapses and explodes, a hypernova represents a more extreme and energetic phenomenon. What sets a hypernova apart is its sheer intensity. The amount of energy released can be over 100 times greater than that of a typical supernova. This colossal explosion is so powerful that for a brief moment it can outshine an entire galaxy, making it visible across vast expanses of space. The sheer magnitude of a hypernova is astonishing. During the explosion, approximately 10% of the star's mass is ejected into space at mind-boggling velocities. This rapid expulsion of matter generates shock waves that ripple through the surrounding interstellar medium, sometimes triggering the birth of new stars. The energy released can even alter the conditions of the surrounding galaxy, influencing the formation of cosmic structures. But perhaps even more fascinating is the connection that hypernovae share with gamma-ray bursts, one of the most violent and energetic phenomena in the universe. Gamma-ray bursts are intense bursts of gamma radiation emitted from distant galaxies, and they are thought to be the result of hypernovae. These extraordinary explosions may give birth to rotating black holes, whose formation releases an immense amount of energy. The energy is focused into narrow jets of particles traveling nearly at the speed of light. As these jets collide with the surrounding space, they generate the gamma-ray bursts that we observe. This association between hypernova and gamma-ray bursts underscores the role these cosmic events play in shaping the universe, not only in terms of their destructive power, but also in their creative potential. Moreover, hypernovae contribute significantly to the chemical evolution of galaxies. These cataclysmic events are responsible for the synthesis of heavy elements such as gold and uranium, which are forged in the hearts of dying stars. The explosive death of a hypernova disperses these elements across space, enriching the interstellar medium. These elements are vital for the formation of new stars, planets, and eventually, terrestrial life as we know it. Thus, while a hypernova marks the end of a star's life, it also plays an essential role in the ongoing cycle of stellar birth and death, contributing to the continuing evolution of the universe. Another extreme and enigmatic remnant of a star's death is the neutron star. These compact objects are among the most bizarre and dense forms of matter in the universe, and studying them has provided some of the most profound insights into fundamental physics. Neutron stars are born from the collapse of massive stars during a supernova explosion. In the aftermath, the core of the star compresses to such an extent that protons and electrons merge to form neutrons, creating a star made primarily of these subatomic particles. The density of neutron stars is almost incomprehensible. A single teaspoon of neutron star material would weigh more than Mount Everest. This remarkable density provides a natural laboratory for testing theories of quantum mechanics, nuclear physics, and general relativity. Under the extreme conditions present within neutron stars, we can study matter in ways that are impossible to replicate on Earth. Neutron stars are also crucial in the study of gravitational waves. The collision of two neutron stars produces ripples in the fabric of space-time, gravitational waves, that were first predicted by Albert Einstein more than a century ago. The observation of these waves confirmed Einstein's theory and opened up a new frontier in astrophysics. One of the most striking features of some neutron stars is their ability to emit regular beams of radiation. These rotating neutron stars, known as pulsars, spin rapidly and emit radiation in narrow beams that sweep across the sky like a cosmic lighthouse. As they rotate, their pulses can be detected from across the universe. Pulsars are incredibly precise, making them invaluable tools for studying gravity, time, and even potential new physics. By observing the regularity of their pulses, scientists can learn about the intense gravitational forces at play near these stars, as well as explore the effects of relativity on time. The study of pulsars also provides a unique opportunity to test theories about the fundamental forces of nature, pushing the boundaries of our understanding. The consistency of their pulse rates allows researchers to challenge our current models of gravity and even search for new phenomena beyond the standard model of particle physics. As research continues, the study of neutron stars promises to unlock new realms of knowledge, potentially reshaping our understanding of matter and energy. Another crucial aspect of modern astronomy is the study of galaxy rotation curves. A rotation curve graphs the orbital velocity of stars and gas within a galaxy relative to their distance from the galactic center. By observing these curves, astronomers have discovered a puzzling discrepancy. While the velocities of stars and gas near the center of galaxies follow the expected laws of motion, those farther out do not slow down as predicted. Instead, they maintain unexpectedly high speeds. This anomaly suggests the presence of unseen mass, which has led to the hypothesis of dark matter. Dark matter is a mysterious and invisible substance that does not emit, absorb, or reflect light, making it nearly impossible to detect directly. However, its existence is inferred from its gravitational influence on visible matter. Dark matter makes up approximately 85% of the total mass of the universe, fundamentally altering our understanding of the cosmos. The study of galaxy rotation curves has provided crucial insights into the distribution of dark matter within galaxies. Often, the shape of the rotation curve suggests that dark matter forms a large, diffuse halo around galaxies. This halo helps stabilize the galaxy, preventing it from flying apart due to the high rotational speeds of the stars at the outer edges. Furthermore, the rotation curves of galaxies reveal the role of dark matter in the formation and evolution of galaxies. Observing how galaxies interact, merge, and evolve over time provides valuable insights into how the presence of dark matter influences the behavior of galaxies. In some cases, the gravitational forces of a merger can trigger the formation of new stars or reshape the galaxy's structure, creating new spiral arms or starburst regions. The galactic halo, which extends far beyond the visible disk of stars, is integral to our understanding of galaxies, including our own Milky Way. This vast region encompasses dark matter, gas, and ancient star clusters known as globular clusters. The gravitational influence of the galactic halo affects the orbits of stars and dictates the overall structure of the galaxy. One of the major mysteries of the galactic halo is the nature of the dark matter it contains. While scientists have yet to detect dark matter directly, its presence is inferred from the way stars move within the halo. If only visible matter were present, stars at the outskirts of the galaxy would not be moving as fast as they are. This discrepancy is the key evidence that suggests dark matter is present in significant quantities. As our understanding of the galactic halo and dark matter continues to evolve, it remains one of the most pressing questions in modern astrophysics. The search for dark matter and the study of its role in shaping galaxies will undoubtedly continue to drive research and discovery in the coming years, as we strive to uncover the secrets of the universe's most elusive substance. The galactic halo, a vast, diffuse region surrounding the Milky Way, holds more than just the remnants of ancient stars. It is a treasure trove of clues that help scientists piece together the story of our galaxy's formation and evolution. Deep within this halo lie ancient star clusters, some of which contain stars that are nearly as old as the universe itself. These clusters are not just relics of the past. They are vital pieces of the cosmic puzzle, offering astronomers an invaluable glimpse into the early phases of galaxy formation. Through these stellar relics, scientists are beginning to understand how the Milky Way grew and changed over time. These clusters, with their ancient stars, offer insights into the conditions that existed in the universe's infancy. By studying them, researchers can trace the interactions between the Milky Way and smaller, more primitive galaxies that once existed in the early cosmos. These interactions helped shape the Milky Way into the grand spiral galaxy we see today, lending the halo its essential role in the story of our galaxy's birth and growth. In recent years, advancements in technology and an increased number of surveys have revealed even more extraordinary phenomena emanating from the halo. Enigmatic bursts of gamma rays and cosmic rays have been detected, hinting at the complex processes occurring in this seemingly quiet region. These high-energy emissions could be tied to the interaction between dark matter and regular matter, providing new possibilities for understanding the fundamental composition of the universe. The discoveries are continuous, each new piece of data adding layers of mystery to the galactic halo. These findings push the boundaries of our understanding, urging scientists to continue exploring and studying this vast and elusive region of space. Among the most captivating of these ancient features are the globular clusters, dense collections of stars that provide a window into the universe's earliest days. The formation of these clusters is a delicate process that involves a variety of fascinating cosmic factors. One of the key players in their creation is the environment in which they form. Globular clusters typically develop in the gravitational fields of galaxies, particularly in their halos. These regions, which contain a combination of high-density matter and a significant presence of dark matter, create the conditions needed for the formation of such clusters. The dark matter in these regions plays a pivotal role by exerting the necessary gravitational pull to keep the clusters together once they begin to form. Additionally, the formation of globular clusters is deeply connected to the early universe. These clusters are among the oldest structures in the cosmos, often containing stars that are almost as old as the universe itself. In fact, the first stars, which were born after the Big Bang, set the stage for the formation of globular clusters. These early stars created the necessary conditions for the birth of heavier elements, which in turn contributed to the formation of subsequent stars. These stars would eventually come together to form the dense clusters we observe today. The formation of globular clusters also has ties to the merging of smaller galaxies. When galaxies collide, they often bring together star systems that can be gravitationally bound into tight clusters. These galactic mergers don't just create new globular clusters, they can also disrupt existing ones, leading to an ever-changing cosmic landscape. This process creates a dynamic and evolving environment where new clusters emerge and older ones are sometimes torn apart, continually reshaping the structure of the galaxy and the halo. In addition to the grand cosmic events that lead to their formation, the dynamical interactions between stars within globular clusters are crucial to their evolution. Over time, these interactions result in the formation of more compact star groups. Gravitational encounters between stars cause some to cluster even tighter, ultimately creating the dense and tightly packed environments that characterize globular clusters today. These interactions, occurring on both large and small scales, create the intricate and complex tapestry of globular clusters scattered throughout the Milky Way and other galaxies. As we delve deeper into the realm of cosmic phenomena, one of the most mind-boggling concepts to emerge is time dilation, a phenomenon predicted by Albert Einstein's theory of general relativity. According to this theory, time behaves not as a constant, but as something malleable and deeply influenced by gravity. When an object is situated near a massive celestial body, such as a planet or a star, the gravitational field slows down the passage of time for that object. The stronger the gravitational pull, the slower time flows. For instance, a clock placed near a black hole will tick more slowly than one placed far from any massive object. A few hours may pass for the clock near the black hole, but much more time could elapse for someone observing it from a distant location. This idea, though mind-bending, has been confirmed through experimental evidence, such as precise atomic clocks, which show that time indeed moves differently depending on the strength of the surrounding gravitational field. The implications of this discovery are profound. Time, once thought to be a constant universal measure, is revealed to be a relative phenomenon, intimately tied to the fabric of space-time and the presence of mass. This challenges the traditional view of time as a steady, unwavering march forward. Instead, it suggests that time is a flexible and dynamic dimension, shaped by the influence of mass and gravity. Grasping this concept not only deepens our understanding of time, but also alters how we perceive the very structure of the universe. It has enormous implications for fields like astrophysics, cosmology, and even the concept of time travel. It also gives us a new lens through which to view the interconnected nature of reality, where gravity influences not just our physical surroundings, but also the passage of time itself. Scientists have long been fascinated by the idea of time travel. Within the framework of modern physics, several different approaches to time travel are being explored. One of the most intriguing ideas comes from Einstein's theories of relativity, which suggests that massive objects can warp the fabric of space-time. This warping opens the possibility for bending time itself, potentially allowing for travel to the past or the future under specific theoretical conditions. Another approach to time travel is based on the concept of wormholes, hypothetical passages through space-time that could connect distant points, both in space and time. If such wormholes exist and could be stabilized, they might provide shortcuts through the fabric of the cosmos, offering a way to travel between different moments in time. Though no experimental evidence has yet confirmed the existence of wormholes, scientists continue to explore whether quantum mechanics could offer a basis for their creation or manipulation. However, the idea of time travel is not without its paradoxes. The grandfather paradox, for example, presents a mind-mind bending dilemma. If someone were to travel back in time and prevent their grandfather from meeting their grandmother, would they still exist in the future? Such paradoxes challenge our understanding of causality, the principle that cause and effect must follow a linear sequence, and raise deep philosophical and scientific questions about the nature of time itself. As researchers continue to explore the possibility of time travel, some have turned to concepts from quantum physics like closed time-like curves, which could theoretically permit a form of time travel. These speculative ideas offer tantalizing possibilities, but they also force us to confront limits of our understanding of space, time, and the fundamental laws that govern the universe. In conclusion, the search for answers to these complex cosmic questions is an ongoing journey. As we explore the far reaches of our galaxy and the mysteries of time itself, we continue to uncover secrets that reshape our understanding of the universe, from the ancient star clusters within the galactic halo to the possibility of bending time. The cosmos offers a never-ending tapestry of challenges and wonders, each discovery pushing us further toward understanding our place in the vast interconnected web of space and time. The concepts of time travel, wormholes, and cosmic strings remain predominantly speculative and theoretical, as they often hinge on conditions and materials far beyond the reach of our current technological capabilities. While the idea of time travel continues to captivate our collective imagination, the practical and theoretical challenges that must be overcome before such phenomena could ever become a reality are immense. At present, our understanding is primarily confined to abstract theories and mathematical models that hint at possibilities, but provide no concrete evidence of feasibility. Among these captivating concepts, wormholes stand out as one of the most fascinating ideas in both scientific and popular culture. Often portrayed in science fiction as shortcuts through the vast expanses of the cosmos, wormholes are theoretical passages that could connect two distant points in spacetime, offering a potential gateway to rapid interstellar travel. These passages, sometimes referred to as Einstein-Rosen bridges, find their roots in Albert Einstein's general theory of relativity, which revolutionized our understanding of how gravity interacts with the fabric of spacetime. In theory, a spacecraft entering a wormhole could travel vast distances across the universe without having to traverse the intervening space. By entering one end of a wormhole, a spacecraft could emerge from the other end, potentially light years away from its original position. While this idea is immensely exciting, it also raises significant scientific hurdles that remain unresolved. Central to the wormhole concept is the need for exotic matter, a theoretical substance with negative energy density, which could keep the wormhole open and prevent it from collapsing under the force of gravity. As of now, there is no experimental evidence to suggest that exotic matter exists, and the concept remains purely hypothetical. Furthermore, the nature of time within a wormhole introduces yet another layer of complexity and intrigue. Some theoretical models suggest that wormholes could potentially allow for time travel, creating the possibility of paradoxes that challenge our conventional understanding of causality. If a traveler were to journey through a wormhole and arrive in the past, it could create contradictions and logical inconsistencies, such as the famous grandfather paradox, where the traveler's actions might prevent their own existence. This intersection of time and space within wormhole theory prompts profound questions about the very fabric of reality and our place within the universe. It ignites debates among physicists and cosmologists who remain both fascinated and cautious in their exploration of such possibilities. Currently, wormholes exist more in the realm of theoretical physics than in practical science, with advancements in quantum mechanics, gravity, and our understanding of the fundamental laws of the universe potentially holding the key to unlocking whether these enigmatic pathways could one day be realized. For now, wormholes continue to inspire both scientific inquiry and the imagination of those who dream of exploring the mysteries of the cosmos, providing a tantalizing glimpse into the potential future of space exploration. Similarly, the concept of cosmic strings adds another layer of complexity to our understanding of the universe. These hypothetical one-dimensional defects in the fabric of space-time are theorized to have formed during phase transitions in the early universe, much like the structures that emerge when water freezes into ice. These cosmic strings, if they exist, would represent enormous, incredibly dense lines that could stretch across vast distances in space. Their existence has not yet been confirmed, but there are intriguing clues that suggest they could be real. The primary evidence for cosmic strings comes from their predicted gravitational effects on surrounding spacetime. If they were to exist, these strings would distort the fabric of spacetime around them, potentially creating detectable gravitational waves. One of the most promising methods for detecting cosmic strings involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. These strings could leave subtle imprints on this radiation, distorting its pattern in a way that would reveal their presence. While current observational data has yet to provide conclusive evidence of cosmic strings, scientists continue to refine their detection techniques, hoping to uncover the faint signatures that might confirm their existence. If cosmic strings were to be detected, their implications for our understanding of the universe would be profound. These objects could serve as cosmic highways, warping spacetime in such a way that they could bend light from distant galaxies, creating distinctive patterns known as gravitational lensing. This effect could offer a new tool for astronomers to study the distant reaches of the cosmos and help reveal more about the early universe's structure and evolution. The presence of cosmic strings could also influence the formation of galaxies, potentially altering the large-scale structure of the universe. Their discovery would force scientists to reconsider many of the fundamental principles that govern spacetime, offering new insights into the nature of reality itself. Meanwhile, the study of cosmic distances and the expansion of the universe continues to play a crucial role in our quest to understand the cosmos. Central to this investigation is the phenomenon known as redshift, which occurs when light from distant galaxies shifts toward longer wavelengths as those galaxies move away from us. The greater the distance between a galaxy and Earth, the faster it appears to be receding. By measuring the redshift of light from distant galaxies and correlating it with their distance, astronomers can gain invaluable insights into the rate at which the universe is expanding. This principle was first observed by the astronomer Edwin Hubble in the early 20th century, when he discovered that galaxies farther away from us were receding at higher speeds, establishing what became known as Hubble's law. This groundbreaking observation suggested that the universe has been expanding since the Big Bang, providing a critical piece of evidence for the theory of an evolving cosmos. The measurement of cosmic distances, particularly through redshift data, has since allowed scientists to develop a more detailed picture of how the universe's expansion has changed over billions of years. Understanding how the universe has expanded over time also offers crucial insights into its ultimate fate. The measurement of redshift helps scientists determine the rate of expansion and how it might evolve in the future. Will the universe continue to expand indefinitely, eventually becoming cold and empty? Or might its expansion slow down and reverse, leading to a big crunch? These are questions that scientists continue to explore, using the tools of observational astronomy and theoretical physics to probe the deepest mysteries of space-time. While much of this research remains speculative, the answers could one day reshape our understanding of the cosmos and our place in it. In all of these areas, time travel, wormholes, cosmic strings, and cosmic expansion, scientists continue to push the boundaries of what we know. Though many of these concepts remain beyond the scope of current technology and understanding, they challenge us to think bigger, to imagine a universe far more complex and mysterious than we ever thought possible. As we advance in our exploration of space and our understanding of the laws that govern it, these enigmatic ideas may one day move from the realm of theoretical physics into the realm of discovery. Until then, they remain an inspiration for the scientific community and a source of wonder for those who gaze up at the stars, dreaming of what might lie beyond. Advancements in distance measurement techniques have significantly refined our understanding of the universe's expansion, helping us unravel some of its most profound mysteries. One of the key methods involves using standard candles, such as Type 2a supernovae, which are stellar explosions that serve as reliable cosmic markers. These explosive events are remarkably consistent in their brightness, which provides a cosmic yardstick for astronomers. By comparing their intrinsic brightness with how bright they appear from Earth, scientists can calculate their distance, offering valuable insights into both the local and distant reaches of the universe. What makes these studies even more astonishing is the realization that the expansion of the universe is not merely happening, but is accelerating. This accelerated expansion has led scientists to propose the existence of dark energy, a mysterious and as yet undiscovered force that might be contributing to the very fabric of the universe. As our ability to measure cosmic distances improves, these precise measurements not only enhance our understanding of the universe's current state, but also provide crucial clues about its ultimate fate. The mysteries of distant galaxies, their interactions, and the forces shaping their evolution come into sharper focus as we peer deeper into the cosmos. Among the most breathtaking cosmic structures revealed by telescopes are the nebula, vast clouds of gas and dust that play a vital role in the life cycles of stars. Some of the most renowned nebulae include the Orion Nebula, the Horsehead Nebula, and the Carina Nebula, each offering not only a mesmerizing visual spectacle, but also a deeper understanding of the processes that govern star formation and stellar evolution. The Orion Nebula, located approximately 1,300 light-years from Earth, stands as one of the brightest nebulae visible to the naked eye. It is often referred to as a stellar nursery, as it is in this dense cloud of gas and dust that new stars are born. The nebula's mass is about 2 million times that of our Sun, and within its boundaries, several young stars shine brightly, illuminating the surrounding gas and creating a stunning kaleidoscope of colors. The study of the Orion Nebula is crucial for understanding star formation and the conditions that lead to the birth of solar systems, offering scientists a glimpse into the early stages of stellar evolution. Similarly captivating is the Horsehead Nebula, located in the constellation Orion. This dark nebula, whose silhouette resembles a horse's head, is set against a backdrop of glowing hydrogen gas. Not only is the image of the Horsehead Nebula one of the most iconic in all of astronomy, but it also offers vital information about the processes occurring within molecular clouds, regions where stars are born. Observing the interactions between light, gas, and dust in the nebula helps astronomers understand the conditions necessary for the ignition of new stars. The Carina Nebula, found in the southern hemisphere, is one of the largest and brightest nebulae. This turbulent region of intense star formation is home to some of the most massive stars known, including Eta Carinae, a variable star notorious for its dramatic fluctuations in brightness. The Carina Nebula is a dynamic environment shaped by powerful stellar winds and the explosive forces of massive stars. These forces mold the surrounding gas and dust, playing a significant role in the overall evolution of the nebula and its constituent stars. Studying the Carina Nebula offers insight into the life cycle of stars and their dramatic influence on galactic evolution. The study of nebulae, such as these, enables astronomers to unravel the complex processes that shape the universe. Through them, we gain a deeper understanding of the formation of stars, the mechanisms that power their birth, and the dramatic impact these stars have on their surrounding environments. This, in turn, allows us to piece together the broader story of cosmic evolution. Stars, in particular, play a pivotal role in shaping our understanding of the universe. Referred to as the building blocks of galaxies, the life cycle of stars offers key insights into the chemical and physical processes that govern the cosmos. The journey of a star begins within a molecular cloud, where gravitational forces cause gas and dust to collapse, eventually forming a protostar. This initial phase is crucial, as it determines the characteristics of the star, including its size, temperature, and lifespan, as well as its eventual impact on the surrounding environment. Throughout their lives, stars engage in nuclear fusion, converting hydrogen into helium in their cores. This process generates vast amounts of energy, producing the light and heat that support life on planets like Earth. However, not all stars follow the same path. Larger stars, in particular, burn through their fuel quickly and end their lives in spectacular supernova explosions. These cataclysmic events are important because they scatter heavy elements like carbon, oxygen, and iron into space, enriching the interstellar medium and allowing for the formation of new stars, planets, and ultimately, life itself. The remnants of stars that explode in supernovae contribute to the ongoing cycle of matter in the universe. When a star exhausts its nuclear fuel, it may leave behind a neutron star, black hole, or white dwarf. These stellar remnants each play a unique role in shaping the evolution of galaxies, and by studying them, astronomers can better understand the origins of elements, the dynamics of galaxies, and the processes that govern the cosmos as a whole. The life cycle of stars also allows scientists to estimate the age of galaxies and, by extension, the universe. Observing stars at various stages of their evolution provides a timeline of cosmic history, allowing astronomers to map the unfolding of the universe over time. This knowledge serves as a powerful reminder that we are part of an ever-evolving universe, intimately connected to the stars that have been burning long before our planet came into existence. One of the most fascinating and extreme types of stellar remnants are magnetars, highly magnetized neutron stars that represent some of the most enigmatic objects in the universe. When a massive star reaches the end of its life and undergoes a supernova explosion, it can collapse into a neutron star, composed almost entirely of tightly packed neutrons. However, in the case of a magnetar, additional processes lead to the creation of incredibly strong magnetic fields. The magnetic field of a magnetar is so intense that it can reach levels up to 1,000 trillion times the strength of Earth's magnetic field, an order of magnitude greater than that of a typical neutron star, which usually has a magnetic field around 1 million times that of Earth. This immense magnetic force is the result of the rapid rotation and collapse of the original star, which amplifies the magnetic field through a process known as the dynamo effect. The extreme conditions present during the formation of a magnetar also contribute to its extraordinary magnetism. The intense magnetic fields of magnetars have a profound impact on their surroundings. They can influence the behavior of nearby matter, even altering the electronic structure of atoms. These magnetic forces can also generate powerful bursts of X-rays and gamma rays, making magnetars one of the most energetic and mysterious objects in the universe. Studying these objects offers scientists a unique window into the extreme physics that govern some of the most extreme environments in the cosmos, providing valuable insights into the nature of matter, energy, and the fundamental forces that shape our universe. Moreover, magnetars, some of the most extreme and enigmatic objects in the cosmos, have the capacity to release bursts of energy known as gamma ray bursts. These bursts occur as a result of the violent rearrangement of their magnetic fields, creating some of the most spectacular high-energy phenomena observable in the universe. For astronomers and researchers, studying the behavior of magnetars provides critical insights into the very nature of the fundamental laws of physics, particularly in the context of extreme states of matter. The incredible magnetic fields within magnetars can be up to 1,000 trillion times stronger than the Earth's magnetic field, making them laboratories for understanding how matter behaves under extraordinary conditions, far beyond anything we encounter on Earth. The discovery and analysis of these bursts push the boundaries of human knowledge and continue to reveal the mysteries of our universe's most powerful objects. Similarly, solar flares, violent eruptions of energy from the sun's surface, release immense amounts of radiation, significantly affecting both space and terrestrial environments. These sudden, violent outbursts of energy can have a profound impact on life here on Earth. Solar flares are capable of sending shockwaves of radiation that can interfere with Earth's magnetic field, leading to geomagnetic storms that disrupt communication networks, GPS systems, and power grids. The energy from a solar flare induces electric currents in power lines, causing widespread blackouts and potentially damaging entire electrical infrastructures. Such events pose not only a threat to technological systems, but also present risks to human life, particularly to astronauts and high-altitude pilots. At higher altitudes, the protective shield of Earth's atmosphere weakens, leaving these individuals vulnerable to the harmful radiation that solar flares emit. As a result, space agencies around the world monitor solar activity more closely than ever. With the advanced technology at their disposal, they are able to detect and anticipate solar flares, issuing early warnings to protect both human and technological infrastructure. However, the effects of solar flares stretch beyond just our technology and our safety. These eruptions can even influence the Earth's upper atmosphere, causing it to expand. This expansion can create drag on satellites orbiting the Earth, altering their paths and reducing their operational lifespans. The increasing density of the atmosphere at higher altitudes can significantly disrupt satellite trajectories, posing a unique challenge for space agencies and satellite operators. Despite these potential hazards, solar flares also give rise to one of the most captivating natural phenomena visible from Earth: auroras. These colorful light displays, often seen near the poles, occur when charged particles from the sun collide with Earth's magnetic field and atmosphere, producing a dazzling light show. While these auroras are a beautiful reminder of the power of solar activity, they also serve as a reminder of how intricately connected solar phenomena are to life on Earth. As humanity continues to advance technologically, the need to better understand solar flares and their far-reaching effects becomes increasingly critical for safeguarding our modern way of life and ensuring the continued success of our space exploration efforts. Moving further into the cosmos, the dark ages of the universe, a term referring to the period following the Big Bang, presents an intriguing and mysterious chapter in the universe's history. This era, lasting from roughly 400,000 years after the Big Bang to approximately 1 billion years later, was marked by the absence of stars and galaxies. During this time, the universe was a vast expanse filled with neutral hydrogen gas with no visible light or complex structures. This primordial era remains one of the most enigmatic periods in cosmology, leaving scientists with a wealth of questions and few concrete answers. While advancements in observational tools have provided some clues about this time, the exact processes that took place during the Dark Ages remain shrouded in mystery, making it a fascinating and active field of research. One of the most captivating mysteries from this time is the formation of the first stars, known as Population 3 stars. These stars were pivotal in ending the Dark Ages and transitioning the universe into a more dynamic state. And they were responsible for producing the first light and synthesizing the heavy elements that would later form planets, and life as we know it. However, the characteristics of these first stars remain a subject of intense debate among scientists. We have yet to detect any direct remnants of these stars, leaving their mass, temperature, and lifespan uncertain. Despite the vast knowledge we have gained about the cosmos, the exact nature of these early stars and their role in the evolution of the universe is still one of the most significant unsolved puzzles in astronomy. In addition to the enigma of the first stars, there is still much to uncover about the density fluctuations in the early universe. These fluctuations are thought to have played a crucial role in the formation of the first galaxies. While the cosmic microwave background radiation provides a glimpse into the early state of the universe, it is still unclear how regions of higher density evolved into the complex structures, such as galaxies, clusters, and cosmic filaments that we observe today. The exact mechanisms by which this transformation took place remain open to exploration, and uncovering these details is crucial for piecing together the broader history of the universe. Furthermore, the era of reionization, which followed the Dark Ages, represents another significant transition in the universe's timeline. During this period, the hydrogen gas in the universe was ionized, allowing light to travel more freely and marking a pivotal moment in cosmic evolution. Understanding the exact timing and processes of this reionization is crucial for understanding the formation of the first galaxies, their growth, and their interactions with the mysterious dark matter and dark energy that permeate the cosmos. This era provides essential insights into the universe's early evolution, shedding light on how the conditions necessary for life came to be. As we turn our attention to the present and future, the challenges involved in sending probes beyond our solar system highlight the extraordinary scale of the universe and the technological limits we must overcome. One of the primary obstacles is the vast distances that separate us from even the nearest star systems. For instance, Alpha Centauri, the closest star system to Earth, is located over 4 light-years away, a distance so great that light itself takes more than 4 years to travel. Current spacecraft, such as Voyager 1, travel at a speed of around 60,000 kilometers per hour, which means that reaching Alpha Centauri would take tens of thousands of years at that speed. Beyond the immense distances, energy requirements present another formidable challenge. Space probes require a reliable power source to continue their missions, and while solar panels can provide energy within the confines of our solar system, they become significantly less effective as they move farther from the Sun. Probes destined for deep space would likely rely on radioisotope thermoelectric generators, which convert the heat generated by the decay of radioactive materials into electricity. These power sources are invaluable for long-duration missions, but they come with their own set of challenges and limitations. Nevertheless, despite the challenges posed by distance and power, the quest to explore beyond our solar system remains one of the most ambitious endeavors of modern science and engineering. As our technology improves, so too does our ability to answer some of the most profound questions about the universe, expanding our knowledge and understanding of the cosmos in ways we could not have imagined just a few decades ago. The journey into deep space and the discoveries it holds will shape the future of humanity's exploration and our place in the vast expanse of the universe. However, the availability of suitable radioactive materials remains a significant constraint, limiting the extent and efficiency with which we can power space missions to distant regions. As we push the boundaries of exploration, these materials become increasingly scarce, creating a bottleneck in powering spacecraft that venture into the unknown reaches of the cosmos. But this is just one part of the equation. Another pivotal challenge lies in communication. As probes journey further into interstellar space, the vast distances they traverse create inherent time delays in signal transmission. A message from a spacecraft located just 1 light-year away takes an entire year to reach us, and similarly, any instructions we send back to the probe take just as long. This delay complicates real-time operations and introduces a new layer of complexity. The spacecraft may need to operate autonomously, relying on pre-programmed instructions and decision-making processes to navigate the vast and inhospitable void. This challenge is compounded by the hostile environment of deep space. Probes, which will travel far beyond the protective shield of Earth's magnetosphere, must be designed to endure extreme temperatures, intense radiation, and constant bombardment by micrometeoroids. Each of these elements poses a direct threat to the sensitive instruments on board the spacecraft. To succeed in these long-duration missions, it becomes essential to develop and deploy materials and technologies that can endure the punishing conditions of deep space. Whether it's designing radiation-resistant shielding or fabricating spacecraft components that can survive the freezing cold of the outer solar system, the obstacles are immense. Nevertheless, each technological breakthrough is a step closer to making interstellar exploration a reality, expanding our reach into regions that were once thought to be beyond human capability. In this context, light sails emerge as a revolutionary technology. By utilizing the momentum of photons, light sails offer a groundbreaking solution to the age-old problem of propulsion. Unlike traditional rockets that rely on burning fuel to generate thrust, light sails harness sunlight itself, an inexhaustible source of energy. These sails, often constructed from lightweight materials such as mylar or advanced composite materials, feature large reflective surfaces that catch sunlight. As the photons exert pressure on the sail, they gradually propel the spacecraft forward. Remarkably, light sails can achieve high speeds without the need for fuel, making them ideal for missions to distant celestial bodies or even for interstellar travel, where conventional propulsion systems would be far too slow and inefficient. The simplicity of light sails extends not only to their design, but also to their operational efficiency. Because these sails are so lightweight and can be constructed from readily available materials, deploying and maneuvering them becomes a more straightforward process compared to traditional spacecraft. These sails can theoretically maintain a continuous acceleration, creating opportunities for spacecraft to reach distant regions of our solar system and beyond in a fraction of the time required by current propulsion technologies. For missions to explore the outer planets or other star systems, this could mean significantly shorter travel times and the ability to carry more sophisticated scientific instruments, all while avoiding the logistical challenges of carrying massive amounts of fuel. The potential of light sails goes beyond just faster travel. They could transform the way we think about space exploration by eliminating the need for bulky fuel supplies. Instead, by converting light pressure into kinetic energy, spacecraft powered by light sails could travel to the furthest reaches of our solar system and beyond. This approach could lead to smaller, more efficient spacecraft, capable of gathering more data while reducing the costs and challenges associated with fuel-dependent missions. As the technology matures, scientists envision missions that could reach neighboring star systems within a matter of decades, rather than the centuries it would take with current propulsion methods. This shift in propulsion technology represents not only an evolution in how we explore, but also a paradigm shift that could drive humanity's long-term ambitions for space exploration. Meanwhile, the search for habitable moons within our solar system continues to fuel both scientific curiosity and hope. What makes these moons so intriguing is the possibility that they may harbor environments capable of supporting life. Scientific theories rooted in the concept of extremophiles, the organisms that thrive in extreme conditions, suggest that life might be far more adaptable than we initially thought. On Earth, life has been discovered in some of the harshest environments imaginable, from superheated hydrothermal vents to the frozen depths of glaciers. If life can survive in such extreme conditions on Earth, why couldn't it exist on other planets or moons, where similar harsh conditions prevail? The study of planetary habitability further guides researchers in their quest to understand what makes a celestial body potentially suitable for life. Factors like the presence of liquid water, a stable temperature range, and available energy sources are essential in determining whether life could thrive on a given moon or planet. For moons such as Europa, Enceladus, and Titan, the possibility of vast subsurface oceans hidden beneath thick icy crust has raised exciting prospects for life. Water, whether in liquid, ice, or vapor form, is often considered a fundamental prerequisite for habitability, and the discovery of such oceans provides a tantalizing glimpse into the potential for extraterrestrial life. Astrobiology, the field that blends biology, chemistry, and planetary science, plays a critical role in this search. Researchers are constantly speculating on the chemical processes that could sustain life beyond Earth. One particularly exciting theory revolves around life utilizing chemical energy from the oceanic hydrothermal vents present on moons like Europa and Enceladus. These hydrothermal vents, akin to those found on Earth's ocean floors, could provide the necessary heat and chemical nutrients to support microbial life in an environment far removed from the warmth and light of the sun. This new perspective encourages scientists to think beyond the traditional reliance on sunlight as the primary source of energy. Instead, it opens the door to alternative ecosystems that do not resemble Earth's surface life. Such possibilities allow for a broader definition of habitability, including environments where life might exist without the need for sunlight or oxygen. Further studies of atmospheric conditions and geological activity on these moons, such as volcanic eruptions or tectonic shifts, can offer additional insights. These geological processes are vital because they might recycle essential materials and provide energy sources, which are crucial for sustaining life over long periods. As scientists continue to refine their understanding of these environments, the search for habitable moons takes on greater urgency. Each discovery moves us closer to answering one of humanity's most profound questions. Are we alone in the universe? The possibilities are vast, and the journey to uncover them is only just beginning. Exploration of moons and distant celestial bodies has long captured the imaginations of scientists and space enthusiasts alike. As we continue to explore the mysteries of our solar system, missions designed to investigate these moons are not only seeking to uncover the conditions of these far-flung worlds, but they are also guiding our understanding of where life might exist beyond Earth. These missions provide the framework for scientists to unravel complex possibilities of extraterrestrial life, pushing the boundaries of what we once thought possible. A critical technique employed in modern space exploration is gravitational assist, also known as gravity assists or slingshot maneuvers. This method is a brilliant way to increase the velocity of spacecraft without the need for additional fuel. By using the gravitational field of a large celestial body like a planet, spacecraft can gain speed as they fly past, harnessing the energy from the planet's motion to propel them further into space. This phenomenon works by carefully exploiting the intricate dance between motion and gravity. When a spacecraft approaches a massive planet, such as Jupiter, it can accelerate dramatically by entering its gravitational field at the right angle and speed. The resulting increase in velocity can enable spacecraft to reach more distant regions, such as the outer planets, their moons, or even the farthest reaches of our solar system, all without the need for costly fuel supplies. The success of this technique can be seen in many remarkable missions. For example, the Voyager spacecraft, which traversed the entire solar system, employed gravitational assists to visit multiple planets and gather invaluable data, vastly expanding our knowledge of these distant worlds. Similarly, the New Horizons mission, which famously passed by Pluto, also made use of a gravitational assist from Jupiter. This maneuver allowed the spacecraft to reach its destination much more quickly than it would have by relying solely on its propulsion systems. Looking ahead, the potential for gravitational assists to aid future space exploration is immense. These techniques will be crucial for achieving ambitious goals, such as landing on distant moons of gas giants or even venturing into interstellar space. By meticulously planning flight paths and optimizing the use of gravity assists, mission designers will be able to push the limits of space exploration, enabling humanity to reach new frontiers and uncover secrets of the cosmos that were once thought unreachable. Over the next decade, a host of extraordinary human space missions are set to unfold, marking the next chapter in humanity's relentless quest to explore the universe. Among the most notable is the Artemis program, which plans to return astronauts to the moon. By 2025, astronauts are set to land on the moon's south pole, where they will conduct groundbreaking research, including searching for water ice. This mission will also establish a sustainable human presence on the moon, laying the groundwork for future journeys to Mars. Artemis is just one step toward furthering humanity's presence in deep space. In parallel, numerous space agencies and private companies are planning human missions to Mars. NASA's ambitious timeline aims for a manned Mars mission by the late 2030s, focusing on understanding the planet's potential for life and exploring its geological history. Private companies, including SpaceX, are pursuing even more aggressive timelines, with some proposing to send humans to Mars sooner. These missions will require cutting-edge technologies and innovations in space travel, pushing the limits of what is possible and testing human ingenuity. Moreover, international cooperation is playing a vital role in preparing for these next-generation missions. One exciting project currently in development is the Lunar Gateway, a space station that will orbit the moon. This station will serve as a staging point for lunar exploration and a platform for deeper space missions. The Gateway will provide astronauts with a base for conducting experiments and research in a unique space environment, helping to prepare for future journeys to Mars and beyond. As engineers and scientists work on these exciting projects, they are also laying the foundations for a future where humanity may not only visit other planets, but may eventually colonize them. The next decade promises to be one of unprecedented advances in space exploration, with the potential to redefine what humankind is capable of achieving in the cosmos. Central to our understanding of life, both on Earth and beyond, are the fundamental conditions that make life possible. These include the presence of liquid water, a stable source of energy, an atmosphere capable of protecting organisms from harmful radiation, and a combination of essential chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Liquid water, in particular, is crucial as it serves as a solvent that facilitates the chemical reactions necessary for life to exist. Equally important are energy sources. On Earth, plants harness sunlight through photosynthesis, while other organisms draw energy from geothermal heat around underwater hydrothermal vents. The atmosphere, too, plays a critical role by regulating temperature and providing the right balance of gases necessary for respiration and photosynthesis. When scientists look beyond Earth, these conditions serve as the criteria for determining whether other planets could support life. Mars, for instance, has long been a focus of astrobiological research due to the evidence of past water flows and ancient riverbeds. Meanwhile, moons like Europa and Enceladus present intriguing possibilities. Both are believed to harbor subsurface oceans beneath icy crusts, environments that could potentially support life. These moons represent some of the most promising locations in the search for extraterrestrial life within our solar system. As the search for life extends beyond our solar system, astronomers are also studying exoplanets, planets orbiting stars outside our solar system. The most promising of these exoplanets are located in what is known as the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. With advancements in space telescopes, we are continually improving our ability to detect and study these distant worlds, assessing their potential to support life as we understand it. In our search for life, the study of extremophiles, organisms that thrive in extreme environments, has provided invaluable insight into the adaptability of life. These remarkable creatures can survive in conditions once thought impossible for life to endure, such as extreme temperatures, high pressures, acidity, or salinity. Some extremophiles, for example, thrive in the heat of hydrothermal vents deep beneath the ocean, where temperatures can exceed several hundred degrees Celsius. These findings challenge our understanding of the conditions necessary for life, suggesting that life may not be limited to the conditions we commonly associate with habitability. The discovery of extremophiles has broadened our search for extraterrestrial life. Instead of limiting our exploration to planets with Earth-like conditions, astrobiologists are now considering a wider array of environments where life could potentially exist. For instance, the subsurface oceans of Europa and Enceladus, worlds that are cold and dark, may harbor microbial life that survives in the most extreme conditions. Extremophiles on Earth serve as a tangible model, helping scientists imagine what life might look like on distant worlds, further expanding our understanding of what is possible in the search for life beyond our planet. This quest to uncover life beyond Earth is not just a pursuit of scientific knowledge, it is a deeper exploration into the nature of existence itself, and it promises to be one of the most profound chapters in humanity's journey through the stars. Extremophiles, organisms that thrive in extreme environments, provide invaluable insights into biochemistry that diverges sharply from the norm. These remarkable life forms rely on unique metabolic pathways using chemical energies drawn directly from their environments. Unlike most organisms on Earth, these metabolic processes do not depend on sunlight or oxygen. This distinction significantly broadens our understanding of what constitutes a viable habitat, extending the potential for life beyond the familiar confines of Earth's conditions. It suggests that life might thrive on planets and moons with very different elemental compositions or atmospheric conditions. Research into extremophiles can thus play a pivotal role in guiding space missions to other planets and moons. These studies can direct us to the most promising sites where life could exist under extreme conditions. For instance, the resilience of extremophiles ignites our imagination, pushing the boundaries of what we think is possible in the evolution of life. If life can emerge and persist in the harshest conditions here on Earth, the probability increases that similar life forms could evolve elsewhere in the universe, in places with extreme environments. This realization opens up new vistas for astrobiology, motivating scientists to explore locations previously overlooked. The lessons we learn from life thriving in Earth's most hostile environments may one day help us discover life beyond our planet. In recent years, some of the most promising locations for extraterrestrial life have been discovered within our own solar system. One of the most compelling sites is Europa, a moon of Jupiter, which is thought to harbor a vast ocean beneath its thick, icy crust. Observations from the Galileo spacecraft, along with more recent studies, suggest that this subsurface ocean could contain more than double the volume of water found on Earth. With the presence of liquid water and the potential for chemical reactions similar to those that sustain life on Earth, Europa stands out as a strong candidate for harboring microbial life. Another intriguing possibility arises from Enceladus, a moon of Saturn. Known for its active geysers that expel plumes of water vapor and organic molecules into space, Enceladus has garnered the attention of scientists searching for life beyond Earth. The Cassini spacecraft detected these plumes, hinting at the presence of a subsurface ocean beneath its icy exterior. Chemical analysis of the plumes revealed simple organic compounds, key building blocks for life. These discoveries sparked the hypothesis that microbial ecosystems could exist within Enceladus's hidden ocean, potentially thriving in conditions similar to those found around hydrothermal vents on Earth. Mars, too, remains a focal point in the search for extraterrestrial life. Evidence of ancient river valleys and lake beds suggests that liquid water once flowed on the red planet's surface. More recently, the discovery of recurring slope lineae, dark streaks that appear and disappear with the seasons, hints at the possibility that briny liquid water might still exist, albeit beneath the surface. Additionally, recent missions have identified organic molecules in Martian soil, expanding the likelihood that life may have existed on Mars in the past, or even that microbial life might persist beneath the surface, dormant but still present. Beyond these moons and planets, our understanding of life itself could be dramatically altered by discoveries of extremophiles that survive under the harshest conditions on Earth, environments with high radiation, extreme temperatures, and high acidity. These organisms challenge our preconceived notions about the limits of life and where it can exist. As technology advances, space missions targeting environments once thought to be inhospitable could yield groundbreaking results. These findings would push the boundaries of our understanding of life's adaptability and its potential presence across the solar system. Understanding ribonucleic acid, RNA, is another critical piece in the puzzle of extraterrestrial life. RNA is fundamental to life on Earth, acting as a messenger that transmits genetic information from DNA to the cellular machinery responsible for protein synthesis. This essential role in biology suggests that any life form, whether terrestrial or extraterrestrial, could share similar biochemical processes. RNA's versatility is particularly intriguing. It can exist in a variety of forms and perform multiple functions, and some researchers even theorize that an RNA world could have existed prior to the emergence of DNA-based life. If this hypothesis proves correct, it opens up the possibility that extraterrestrial life might also rely on RNA as a fundamental molecule. The search for RNA beyond Earth holds the promise of expanding our understanding of life itself. By identifying environments in space where RNA could form and survive, scientists can better target their search for signs of life. This exploration also challenges traditional concepts of life. Scientists are investigating how alternative biochemistries, such as those based on elements other than carbon, could support life in extreme environments. The discovery of non-carbon-based analogs of RNA would radically shift our understanding of habitability, allowing for the possibility of life forms that could exist in environments vastly different from Earth. This broadens the scope of our search for life, not just to Earth-like planets, but to a far wider range of celestial bodies, each with its own unique set of conditions. Ultimately, extremophiles and RNA play an essential role in shaping the future of astrobiology. They expand our notion of what is possible, transforming how we search for life in the universe and challenging our assumptions about the nature of life itself. With every new discovery, we inch closer to understanding not only where life could exist beyond Earth, but also the broader question of how life evolves, adapts, and persists across the cosmos. The search for life beyond Earth has captivated the human imagination for centuries, and recent missions to Mars, as well as the icy moons of Jupiter and Saturn, are bringing us closer than ever to unlocking the mysteries of extraterrestrial existence. As scientists explore these distant worlds, they carry out experiments designed to detect nucleic acids or their building blocks, key components of life as we understand it. By recreating extraterrestrial conditions in laboratories here on Earth and analyzing samples from celestial bodies, they hope to detect traces of RNA. This simple molecule could serve as a crucial indicator of whether life, either past or present, exists or has existed elsewhere in the universe. The implications of such discoveries could radically transform our understanding of life's origins, not only on our own planet, but across the cosmos. When we look for signs of life within our solar system, several locations stand out as particularly intriguing. Mars, for example, has long been the focus of scientific exploration, thanks to its historical connection to liquid water and evidence suggesting that the planet once had a more temperate, habitable climate. Recent missions have uncovered ancient riverbeds, lake deposits, and even subsurface ice. These discoveries hint at Mars' potential to harbor microbial life, either in the distant past or even today. The search for life on Mars hinges on the possibility that microbial organisms could have survived in protected niches beneath the planet's surface, making it a prime candidate in our ongoing quest to find extraterrestrial life. Equally captivating is Europa, one of Jupiter's many moons. Beneath its frozen, icy crust lies a vast liquid ocean, which may be in direct contact with the moon's rocky mantle. This unique environment could offer the chemical reactions necessary for life to thrive. Moreover, scientists believe that plumes of water vapor which erupt from Europa's surface could provide a direct pathway to study the moon's subsurface ocean. This makes Europa an essential target for future missions, as scientists seek to uncover potential signs of life hidden deep beneath the ice. Enceladus, another of Saturn's moons, also holds great promise. Like Europa, it has a subsurface ocean concealed beneath a thick layer of ice. Observations from the Cassini spacecraft revealed geysers erupting from the surface, shooting water vapor and organic molecules into space. The discovery of these building blocks of life in the plumes suggests that Enceladus may offer a potentially habitable environment beneath its icy shell. This revelation has propelled Enceladus to the forefront of scientific inquiry as a key prospect in the search for biological signs within our solar system. Then there is Titan, Saturn's largest moon. Titan challenges our conventional notions of habitability. Unlike Earth, Titan's surface is covered with lakes and rivers made of liquid methane and ethane, and its thick, nitrogen-rich atmosphere is teeming with complex organic compounds. While Titan's conditions differ drastically from those on Earth, its intricate chemistry raises the fascinating possibility that life could exist in forms completely unlike anything we know, thriving in a liquid environment based not on water, but on methane. This possibility ignites our curiosity about what life forms could look like under such alien conditions. Each of these celestial bodies provides a unique window into the vast potential for life to exist elsewhere in the universe. As we look beyond our planet, these discoveries open new doors to understanding where life could thrive, expanding the possibilities of what we might find in the cosmos. The Voyager missions, launched in the late 1970s, have played a significant role in expanding our knowledge of the outer solar system. Voyager 1 and Voyager 2, as they journeyed toward the distant reaches of our solar system, delivered a treasure trove of data about the gas giants and their myriad moons. Both spacecraft were equipped with cutting-edge instruments designed to capture stunning images, analyze the atmospheric compositions of the gas giants, and measure magnetic fields. These contributions significantly expanded our understanding of these remote, enigmatic worlds. One of the most remarkable findings from the Voyager missions involved the intricate and dynamic atmospheres of Jupiter and Saturn. For example, Voyager's close encounters with Jupiter revealed the Great Red Spot, a massive, centuries-old storm that is larger than Earth itself. This discovery demonstrated the complex meteorological patterns shaping the gas giant's atmosphere. Notably, Voyager also unveiled the existence of faint ring systems around both Jupiter and Saturn, providing further evidence that these colossal planets are not just featureless giants, but rather intricate worlds with their own unique satellite systems. The Voyager missions also made significant contributions to our understanding of the moons of these planets. For instance, Voyager 2's flyby of Uranus revealed that the planet had an unusual tilt, and it also discovered dark rings previously unknown to science. Perhaps one of the most striking revelations came from Voyager's observations of Triton, Neptune's largest moon. The spacecraft uncovered geysers spewing from Triton's surface, suggesting the presence of subsurface activity, a potential indication of a more complex geological history than scientists had previously imagined. These monumental discoveries, driven by the legacy of the Voyager missions, continue to fuel our curiosity and deepen our understanding of the outer reaches of our solar system. With each new revelation, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? As we send more probes and missions into the unknown, the possibility of finding life, or at least signs of life, on other worlds becomes ever more tangible, opening up exciting new frontiers in the search for life beyond Earth. These space missions have profoundly enhanced our understanding of the cosmos, revealing intricate dynamics that govern the environments of distant planets. With the launch of the Voyager spacecraft, humanity embarked on an unprecedented journey to explore the outer reaches of the solar system. The data gleaned from these missions, especially regarding the magnetic fields surrounding distant planets, provided groundbreaking insights. These magnetic fields, which interact in complex and mysterious ways with their respective environments, unveiled phenomena that helped define planetary atmospheres. What Voyager uncovered has propelled research, shaping future explorations of these enigmatic regions. Its findings have offered a clearer picture of the vast, intricate complexity of our solar system, inspiring generations of scientists to push the boundaries of space exploration further. The impact of these spacecraft continues to resonate in the scientific community today, as we attempt to piece together the nature of the solar system's distant members. The magnetic interactions observed by Voyager have also contributed to a deeper understanding of planetary protection mechanisms, highlighting the delicate balance of forces that shape not just atmospheres, but the very conditions that make life possible, if life can exist at all. These discoveries have proven to be pivotal in fueling subsequent missions that seek to understand the origins of life and the environmental conditions that might support it. In parallel, the Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance, have similarly revolutionized our comprehension of the Red Planet. Equipped with cutting-edge scientific tools, these robotic explorers were tasked with one of humanity's most pressing questions: could Mars ever have supported life? The rovers' results were nothing short of transformative. The barren landscape of Mars, long thought to be incapable of supporting life, has revealed itself to have once been much more hospitable. Mars wasn't always the arid, cold desert it is today. In its distant past, it had conditions that may have been suitable for life, especially microbial life. Discoveries of ancient riverbeds, lakes, and minerals like clay, which typically form in the presence of water, hint at a much wetter, warmer Mars. Curiosity, for instance, uncovered a series of geological formations that provided compelling evidence of past bodies of water. These findings strongly suggest that billions of years ago, microbial life could have potentially thrived in the Martian soil. The exploration didn't stop at geology. The rovers also made significant strides in detecting organic molecules, complex carbon-based compounds that form the building blocks of life. Though the presence of organic molecules doesn't definitively prove that life once existed on Mars, it suggests that the chemical processes necessary to support life may have occurred there. Perseverance, the most recent rover, is specifically tasked with collecting samples that could one day be brought back to Earth for further analysis. This research is central to the ongoing quest to understand Mars's habitability and its potential to harbor life, past or present. These findings have reshaped our approach to searching for life beyond Earth. Mars is now considered a prime candidate in the search for extraterrestrial life. Its history, its geology, and the clues left behind in its landscape have opened up exciting new possibilities about the nature of life itself, prompting debates in the scientific community. Could life exist elsewhere in the universe? And if so, what forms might it take? As we probe deeper into the mysteries of Mars, we begin to question whether life, in some form, might be more resilient and widespread than previously imagined. The lessons learned from these missions are invaluable, offering insights not just about the planets we study, but about the very essence of space exploration itself. Each mission, whether marked by triumph or setback, has expanded our understanding of technology, science, and the complexities of venturing into the unknown. The Voyager missions, for example, showed us how far robust engineering could take us, enduring the harsh environments of space. Voyager's ability to maintain communication over such vast distances became a milestone in long-range communication, inspiring subsequent advancements in this field. Yet failures too have played their part. The tragic loss of the Mars Climate Orbiter, caused by a simple but critical error, a miscommunication between metric and imperial measurements, underscored the importance of precision and rigorous testing. This incident reinforced the need for clear communication and careful planning, lessons that have been incorporated into subsequent mission protocols. Failures, however, don't always spell the end. The story of the Hubble Space Telescope is a prime example. Originally launched with a flaw in its optics, the Hubble was nearly deemed a failure. But human ingenuity stepped in and repairs were made, transforming the telescope into one of the most powerful tools for studying the universe. Hubble's subsequent discoveries, from distant galaxies to the birth of stars, revolutionized our understanding of cosmic phenomena. Its story stands as a testament to the power of innovation and perseverance, reminding us that even after setbacks, recovery and progress are possible. These experiences have shaped the culture of space exploration. They have taught us to approach challenges with a combination of meticulous planning and the flexibility to adapt when things go wrong. Each success and failure adds to our growing knowledge, refining the practices we use and laying the groundwork for the missions of tomorrow. The Apollo missions, for example, completely transformed our understanding of human space exploration. Before Apollo, human space travel was largely theoretical, confined to low Earth orbit. But Apollo proved that humans could survive and thrive beyond Earth. With the success of Apollo 11, astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface, a moment that would forever change humanity's relationship with space. The technological advancements driven by Apollo were immense. The development of life support systems, navigation technology, and heat shields made it possible for astronauts to travel safely through space and return to Earth. The lessons learned during Apollo did not just benefit lunar missions, but also laid the foundation for future space programs, including the Space Shuttle and the International Space Station. Apollo also sparked a wave of technological innovation that continues to resonate in engineering fields today. The Apollo program showed us what was possible when humanity united to tackle one of the greatest challenges of the 20th century. Ultimately, space exploration is about more than just answering questions. It's about expanding our capabilities, pushing the boundaries of what we know, and inspiring future generations to continue reaching for the stars. Each mission, each discovery, and each challenge contributes to a larger understanding of not just the universe, but of ourselves and our place within it. With every success and every failure, we move closer to answering some of the most profound questions about life, the universe, and our future among the stars. The Apollo missions, emblematic of the intense geopolitical rivalry of the Cold War, transcended their immediate national significance to become defining moments in humanity's quest for space exploration. Set against a backdrop of global tension, these missions were not merely technological triumphs. They were emblematic of the broader ambitions of nations to assert themselves as leaders on the world stage. The space race, charged with the spirit of competition and cooperation, was ultimately a testament to human resilience, ingenuity, and the shared vision of reaching beyond our planet. Yet, beyond the immediate geopolitical context, the Apollo missions had a lasting impact on the narrative of human exploration. They sparked a collective imagination, igniting a desire for discovery that has continued to shape our ambitions in space exploration. Their legacy laid the groundwork for the future, fueling interest in the exploration of Mars and other celestial bodies. The missions reaffirmed the indomitable human desire to push the boundaries of what is possible, forever altering the trajectory of space exploration and ensuring that humanity's pursuit of knowledge would continue to evolve. Among the most significant milestones in modern astronomy is the discovery of exoplanets, with the Kepler Space Telescope at the forefront of this revolution. Before Kepler's groundbreaking mission, the idea that planets could exist outside our solar system was largely speculative, based on limited evidence and the detection of only a handful of candidates. However, with the launch of Kepler in 2009, astronomers were equipped with the tools needed to systematically detect and catalog distant worlds. Kepler's methodology, employing the transit method, involved monitoring the slight dimming of starlight as planets passed in front of their host stars, a technique that allowed the detection of thousands of new exoplanets. One of the most striking revelations from Kepler's data was the extraordinary variety of planetary systems discovered. Scientists found worlds ranging from planets that were similar in size to Earth to gas giants vastly larger than Jupiter. Some exoplanets orbited their stars at distances comparable to those of Mercury or Venus from our Sun, which challenged existing theories about planetary formation and migration. These discoveries forced scientists to rethink our understanding of planetary system dynamics and raise profound questions about how unique our solar system truly is. Perhaps the most significant impact of Kepler's discoveries was its role in identifying planets that lie within their star's habitable zone, the region where conditions might allow for liquid water to exist on a planet's surface. This finding was a game changer, sparking an intense scientific interest in the search for extraterrestrial life. The notion that life could potentially exist elsewhere in the universe became not just a matter of speculation, but a scientific pursuit grounded in data and observation. As a result, future missions were designed to explore these habitable exoplanets further, with the goal of studying their atmospheres and chemical compositions to uncover any potential signs of life. Kepler's legacy is profound, not only for the wealth of data it provided, but for the new avenues it opened in the study of exoplanets and planetary science. By expanding the catalog of known exoplanets to over 4,000, it essentially created a new field of research, one that continues to thrive as astronomers seek to understand the diverse environments of distant worlds. Kepler's discoveries have fundamentally altered our perception of the cosmos and spurred a new era of exploration, one where the search for life beyond Earth is no longer a distant dream, but an attainable goal. In the wake of Kepler's success, several next-generation observatories and telescopes are poised to revolutionize our understanding of the universe. Among the most eagerly anticipated is the James Webb Space Telescope, set to launch in the near future. Unlike its predecessor, the Hubble Space Telescope, which primarily observes visible light, the James Webb will focus on infrared wavelengths. This ability to detect infrared light will allow Webb to peer through the cosmic dust clouds that obscure the birth of stars and planetary systems, providing an unprecedented view of the universe's earliest galaxies, those formed in the aftermath of the Big Bang. With its innovative technology, the James Webb is expected to answer some of the most pressing questions in astrophysics, particularly regarding the formation of stars, the evolution of galaxies, and the potential for life beyond Earth. Another cutting-edge project, the Extremely Large Telescope, ELT, will soon take its place atop the Paranal Mountains in the Atacama Desert of Chile. With a mirror spanning an extraordinary 39 meters, it will become the largest optical telescope ever constructed. Equipped with a suite of advanced instruments, the ELT will be capable of studying the atmospheres of exoplanets in unprecedented detail. One of its primary goals is to search for biosignatures, indicators of life, in the atmospheres of distant worlds. Additionally, the ELT will probe some of the universe's most fundamental mysteries, such as the nature of dark matter and dark energy, which continue to elude our understanding. Meanwhile, the Square Kilometer Array, SKA, a groundbreaking radio telescope project, is set to enhance our understanding of the cosmos in ways never before imagined. Spanning thousands of antennas across Australia and South Africa, this vast observatory will have the sensitivity and resolution necessary to study phenomena such as black holes, neutron stars, and the very fabric of space-time itself. With its ability to survey the universe at an unprecedented scale, the SKA is expected to uncover new insights into the origins of galaxies and the forces driving cosmic evolution. Together, these future missions represent the next chapter in humanity's unyielding pursuit of knowledge. As we look outward, our understanding of the universe continues to expand, offering new revelations about the fundamental forces of nature, the origins of life, and our place in the vast cosmic expanse. The legacy of the Apollo missions, Kepler, and the emerging technologies of tomorrow marks the beginning of a new age in space exploration, one where the search for life, the exploration of distant worlds, and the quest to understand the universe are not merely scientific endeavors, but defining pursuits of human curiosity and ambition. As humanity embarks on a new chapter of space exploration, the Lunar Gateway, part of a broader and more ambitious endeavor encompassing lunar exploration, emerges as a cornerstone. Positioned strategically in orbit around the Moon, this infrastructure will serve as a launching point for humanity's next great scientific leap. Beyond its function as a gateway to lunar missions, it will also provide a unique vantage point for astronomical observations from space. Free from the interference of Earth's atmosphere, the Gateway promises a pristine environment for observing distant celestial bodies. This unprecedented platform will house a variety of next-generation telescopes capable of observing phenomena beyond the reach of ground-based instruments. With the Moon acting as an ideal observatory site, scientists will have the opportunity to conduct research into the fundamental dynamics of the universe. What was once constrained by the limitations of Earth-bound technology will now be accessible in ways that could revolutionize our understanding of the cosmos. Each new telescope arriving at the Gateway will contribute to a fresh frontier in cosmology, one where the mysteries of the universe, such as the origins of black holes or the nature of dark matter, are waiting to be uncovered. In this new era of astronomical exploration, the role of artificial intelligence, AI, cannot be overstated. The sheer volume of data generated by telescopes and space missions each year is staggering, from high-resolution images of galaxies billions of light-years away to spectral data that reveals the chemical composition of distant stars. The amount of information produced is often overwhelming. Traditionally, this data would be beyond the processing capacity of human researchers. However, AI now steps in as a powerful tool for analyzing this colossal sea of information. Machine learning algorithms have the ability to sift through vast data sets with incredible speed and precision. These systems can rapidly identify patterns or anomalies that might otherwise go unnoticed by human eyes. For instance, AI can detect transient cosmic events such as supernovae or gravitational waves, phenomena that occur in fleeting moments across the timeline of the universe. Such events, often visible only for brief instances, are hard to capture with traditional methods. AI, however, excels at catching these ephemeral occurrences and flagging them for further investigation. Moreover, AI's capabilities extend to image recognition, allowing scientists to classify celestial objects with remarkable accuracy. Differentiating between stars, planets, and galaxies becomes a matter of processing large volumes of image data, which AI can handle far more efficiently than manual analysis. What's more, as AI systems are continuously fed with new data, their predictive capabilities improve. Over time, they learn to identify subtle correlations, sometimes suggesting new hypotheses or research directions that human scientists might not have previously considered. The applications of AI go beyond mere observation and classification. Projects focused on the search for extraterrestrial intelligence, SETI for example, benefit immensely from AI's ability to process vast streams of radio signals in real time. By analyzing these signals with greater speed and accuracy than ever before, AI could be the key to unlocking the first signs of intelligent life beyond our planet. As AI technology continues to evolve, its role in cosmology is only expected to grow, transforming the way scientists approach their research and accelerating discoveries at a pace previously thought unimaginable. As we look forward, space agencies around the world are also dedicating significant resources to the exploration of asteroids and comets, unlocking new opportunities for scientific breakthroughs. These objects, remnants from the early solar system, hold crucial information about the conditions that led to the formation of planets and life itself. New technologies are allowing us to study them like never before, leading to insights that could change everything we know about our own origins. One of the most promising areas of advancement involves spacecraft and instruments designed specifically for asteroid exploration. Missions like NASA's Double Asteroid Redirection Test, DART, are testing planetary defense technologies by altering the trajectory of asteroids. These groundbreaking missions rely on cutting-edge navigation and imaging technologies, enabling them to observe and analyze their targets in unprecedented detail. The data collected will offer valuable insights not just into the technology of planetary defense, but also into the physical properties of asteroids themselves. Another area of innovation involves remote sensing techniques. New spectrometers and imaging devices allow scientists to study the surface compositions of asteroids and comets from afar. These instruments can detect organic molecules, water ice, and other key building blocks of life, shedding light on the early conditions of our solar system and the potential for life elsewhere in the universe. The combination of infrared and visible light observations allows for a comprehensive analysis of these celestial bodies, revealing their chemical makeup, physical structure, and evolutionary history. Robotic landers and sample return missions are also revolutionizing our approach to asteroid exploration. Missions such as Japan's Hayabusa and NASA's OSIRIS-REx have demonstrated the potential of sending spacecraft to land on distant celestial bodies, collect samples, and return them to Earth for analysis. These missions employ highly sophisticated collection mechanisms and precise landing technologies, enabling them to target specific geological features and gather invaluable data on the composition of asteroids. The future of asteroid exploration is also being shaped by the development of smaller, more agile spacecraft, known as CubeSats. These compact, cost-effective satellites can be launched as secondary payloads alongside larger missions, greatly expanding our observational capabilities. Their small size and high maneuverability allow for data collection from multiple angles, offering new perspectives on the behavior and characteristics of asteroids and comets in our solar system. Looking ahead to the next decade, the study of exoplanets, the countless planets orbiting stars beyond our own solar system, holds enormous potential to transform our understanding of the universe. As telescope technology continues to improve, astronomers will gain access to more sophisticated instruments that can provide unprecedented views into the atmospheres and compositions of distant exoplanets. Projects like the James Webb Space Telescope, which is set to launch in the near future, are expected to offer some of the deepest and most detailed observations of exoplanetary systems ever made. By studying the atmospheres of these distant worlds, scientists will gather vital clues about their potential for habitability. In addition to better instruments, new observational techniques such as transit photometry and radial velocity methods have led to an explosion in the discovery of exoplanets. These breakthroughs are providing a wealth of new data, allowing researchers to refine their understanding of how planets form, migrate, and evolve over time. As astronomers compile data on an increasingly diverse range of exoplanets, ranging from gas giants to rocky Earth-like worlds, they will continue to reshape our understanding of what constitutes a habitable environment. Exciting new avenues of exploration will also focus on studying the weather and surface conditions of these exoplanets. By analyzing the light that reflects off their surfaces, scientists will gain insights into their geology and chemical composition. These studies not only enhance our knowledge of distant planets, but they also force us to rethink the characteristics of our own solar system. What if exoplanets possess features we've never observed before? Strange and unfamiliar conditions that challenge our current understanding of planetary science. With each new discovery, the boundaries of our knowledge continue to expand, revealing that the universe is far more diverse and complex than we ever imagined. The possibilities for groundbreaking advancements in artificial intelligence and data processing have the potential to radically transform our ability to analyze exoplanetary data. Imagine algorithms capable of sifting through enormous data sets, patterns emerging that once seemed invisible. The speed and precision at which AI can process data means that we might uncover insights about distant worlds that were previously out of reach. These technological breakthroughs could not only answer long-standing questions, but could also spark new waves of curiosity, prompting us to rethink the very nature of life in the cosmos. What if, as we delve deeper into the mysteries of the universe, we begin to uncover answers that reshape our understanding of existence itself? At the heart of this exploration lies the concept of colonizing other planets, a prospect that holds immense transformative potential for our scientific knowledge. Venturing beyond Earth offers more than just the chance to set up new settlements. It provides a unique opportunity to test the limits of human biology, to observe how life might adapt and evolve in entirely foreign environments. Take, for example, the idea of establishing a permanent base on Mars. Such an endeavor would give scientists an unparalleled opportunity to examine how human biology responds to altered conditions: lower gravity, different radiation levels, and a radically different atmosphere. What we learn from such experiences could revolutionize medicine and biology here on Earth, offering insights into how we might address health challenges that have long been considered insurmountable. But the benefits of space exploration don't stop with biology. By setting up a base on another celestial body, we would gain the opportunity to conduct long-term observations of cosmic phenomena without the interference of Earth's atmosphere. From solar flares to meteor showers, such observations would allow us to study celestial events in unprecedented detail. These insights could lead to significant breakthroughs in astrophysics, allowing us to refine and expand our models of the universe. Moreover, the very act of constructing advanced instruments in space would dramatically enhance our ability to collect data, potentially providing answers to some of the most profound questions in modern science, such as the nature of dark matter and dark energy. These mysteries, which have puzzled scientists for decades, could become far less elusive as our tools for investigation grow more powerful. The challenges involved in sustaining human life on another planet would also drive the development of innovative technologies. Life support systems, sustainable agriculture in harsh environments, and planetary engineering would all be critical areas of research. The technologies developed to ensure human survival in space could have far-reaching applications on Earth. In the context of climate change and dwindling resources, the lessons learned from creating closed-loop ecosystems and sustainable living conditions on distant planets could provide valuable solutions here at home. These innovations could help us rethink the way we approach resource management, energy production, and environmental sustainability, potentially sparking a new wave of scientific investigation aimed at addressing some of the most pressing challenges of our time. Yet, perhaps one of the most profound aspects of space colonization is its cultural and philosophical implications. The very act of living on another planet compels us to rethink our place in the universe, to challenge our assumptions about what it means to be human. As we push the boundaries of exploration, we are simultaneously confronted with questions about our responsibilities, not only to other worlds, but also to our own. Colonization forces us to reflect on our stewardship of Earth and consider how our actions today might shape the future of humanity. This shift in perspective could fundamentally alter our scientific priorities and ethical considerations. As we venture into space, we must also grapple with questions about the nature of life, consciousness, and our role in the larger cosmic tapestry. Speaking of the cosmos, the planet Uranus presents a fascinating enigma that continues to captivate scientists and astronomers alike. Beyond its striking blue-green color and its impressive collection of rings and moons, Uranus is unique for its peculiar rotation. Unlike most planets which rotate on an upright axis, Uranus spins on its side, with an axial tilt of approximately 98 degrees. This unusual orientation causes the planet to roll along its orbit like a giant bowling ball, making Uranus one of the most distinctive planets in our solar system. The question, of course, is, why does Uranus rotate in such a strange way? Several theories have been proposed to explain this oddity. One of the most widely accepted explanations suggests that Uranus experienced violent collisions with other celestial bodies during its formation. These impacts, which may have been powerful enough to shift the planet's axis, could have caused Uranus to tilt dramatically. This theory is supported by simulations of the early solar system, which show that gravitational interactions with other large bodies could have contributed to Uranus's current orientation. Another possible explanation involves the planet's moons and rings. Although the gravitational pull of these celestial bodies is much weaker than that of a major impactor, the cumulative effect of their gravitational interactions over millions of years could have gradually nudged Uranus into its tilted position. Whether through collisions or gradual gravitational shifts, the end result is the same. Uranus's unique rotation continues to intrigue scientists, offering a window into the dynamic and often chaotic processes that shaped the early solar system. As we continue to study these celestial bodies and explore the mysteries of space, we are constantly reminded that the universe is full of surprises, many of them beyond our current understanding. From the potential of AI to revolutionize exoplanetary research, to the challenges and opportunities presented by space colonization, the future of space exploration promises to push the boundaries of science, philosophy, and human ambition in ways we are only beginning to imagine. Each discovery not only brings us closer to understanding the cosmos, but also challenges us to rethink our place within it. Uranus, a planet unlike any other in our solar system, has long captivated scientists with its peculiar features. Most notably, the planet's extreme axial tilt remains one of the most intriguing mysteries in planetary science. While many hypotheses have been proposed to explain this unusual feature, one of the most compelling suggestions is that it may not have been caused by an external impact, as was once believed, but rather by the way Uranus itself formed. If Uranus had a unique formation history involving a dense disk of material from which it accreted, this could have influenced the planet's tilt. Such a formation process, distinct from the typical planetary development, could be the key to understanding why Uranus rotates on its side in such an eccentric manner. Despite the various theories, the exact cause of Uranus's strange rotation remains unresolved, continuing to intrigue astronomers and scientists as they work tirelessly to decode the planet's enigmatic nature. The subject of planetary rings is another fascinating aspect of planetary science, providing insights into the complex gravitational interactions within our solar system. Most planetary rings form from the debris of moons, comets, or asteroids that stray too close to a planet and are torn apart by its immense gravitational forces. This process takes place within a specific region known as the Rush limit, where the tidal forces exerted by the planet are stronger than the internal forces holding these smaller bodies together. As a result, the debris spreads out, forming a thin, elegant ring system that encircles the planet. The materials that make up these rings vary depending on the composition of the disintegrated bodies, with many rings composed of ice particles intermixed with rocky debris and dust. The reflective properties of ice contribute to the dazzling, shimmering appearance of these rings, as seen most notably around Saturn. However, not all planetary rings are created equal. Some rings are densely packed with material, while others are far more diffuse. This variation leads to an array of stunning visual effects, from densely structured bands to diffuse ethereal halos. The size and strength of a planet's gravitational field, along with its proximity to the sources of debris, are crucial factors in determining the prominence and dynamics of its rings. Gas giants like Saturn, Jupiter, Uranus, and Neptune, due to their substantial mass and advantageous location in the solar system, have the ability to capture and retain vast quantities of material from nearby asteroids or moons, allowing them to sustain vibrant and dynamic ring systems. Furthermore, the longevity of these rings is often maintained through a continuous cycle of material replenishment, as smaller bodies are captured by the planet's gravity and pulled into the rings where they are torn apart. The discovery of rings around these gas giants has revealed the delicate balance between gravity and the composition of surrounding materials. While Saturn's rings are undoubtedly the most famous and widely studied, the rings around other gas giants also present an array of unique and complex features that highlight the diversity of celestial phenomena in our solar system. The rings serve as a record of the interactions between a planet and its environment over time, offering clues about planetary evolution and the history of our cosmic neighborhood. One of the most significant advancements in our understanding of planetary rings came from the Cassini-Huygens mission, which entered orbit around Saturn in 2004. The Cassini spacecraft delivered an abundance of unexpected discoveries that revolutionized our understanding of Saturn and its moons. Among the most astonishing revelations were the intricate dynamics within Saturn's rings. Scientists discovered that the rings were not only shaped by the gravitational forces of Saturn itself, but also by the influence of tiny moons, known as moonlets, embedded within the rings. These moonlets create gaps, waves, and other features within the rings, adding layers of complexity to the system. The discovery of these moonlets provided new insights into the formation and evolution of ring systems across the solar system. Enceladus, one of Saturn's largest moons, became a focal point for astrobiological studies during the Cassini mission. The spacecraft detected plumes of water vapor erupting from the moon's southern pole, indicating the presence of a subsurface ocean beneath its icy crust. The possibility that Enceladus harbors liquid water raises intriguing questions about the potential for life beyond Earth. Further analysis of the plumes revealed organic compounds, making Enceladus an even more tantalizing target for scientists exploring the possibility of microbial life in the outer solar system. Titan, Saturn's largest moon, also became a major subject of scientific inquiry. With its thick atmosphere and lakes of liquid methane and ethane, Titan presents a stark contrast to Earth. The discovery of these methane lakes was particularly surprising, as scientists had expected the moon's surface to be barren and icy. Titan's unique environment, marked by its frigid temperatures and chemical richness, has prompted researchers to reconsider what forms of life might exist under such extreme conditions. Could alternative biochemical processes take place on Titan, giving rise to life forms that function in ways we have yet to imagine? Beyond the moons and rings, Cassini's exploration of Saturn also revealed surprising insights into the planet's magnetic field and its interaction with the solar wind. These findings shed new light on the nature of Saturn's magnetosphere, showing that the planet's magnetic environment is far more dynamic and intricate than previously understood. This deepened our understanding of how planetary magnetic fields interact with the solar wind and shaped the broader understanding of planetary magnetospheres throughout the solar system. Each of these groundbreaking discoveries not only expanded our knowledge of Saturn and its moons, but also sparked new questions about the potential for life elsewhere in the solar system. These findings underscore the importance of continued exploration and the need to look beyond Earth to understand the possibilities for life in the universe. Turning to the Sun, we are reminded that it is the central star of our solar system, providing the energy and gravitational pull that sustains life on Earth. The Sun's immense gravitational field keeps the planets in their orbits, and its energy is essential for driving the climate, weather patterns, and many biological processes on our planet. The intensity of solar radiation decreases with distance from the Sun, which leads to strikingly different climates on the planets. The closer a planet is to the Sun, the more solar energy it receives, and the hotter its surface tends to be. For instance, Mercury and Venus, the closest planets to the Sun, experience extreme heat, while Earth, located at just the right distance, maintains a temperate climate conducive to life. The Sun's energy is also crucial for the process of photosynthesis, which sustains life on Earth by enabling plants to convert sunlight into food. Furthermore, the Sun's energy influences global weather patterns, ocean currents, and atmospheric circulation, all of which are vital for maintaining Earth's climate. The tilt of Earth's axis is another key factor that shapes our climate, causing seasonal variations as different regions receive varying amounts of solar radiation throughout the year. Beyond the inner planets, the outer planets, such as Jupiter and Saturn, experience far less solar energy due to their greater distance from the Sun. As a result, these planets have vastly different climates. For example, Jupiter, despite being far from the Sun, exhibits complex atmospheric phenomena, such as the Great Red Spot, a massive storm that has been raging for centuries. This storm is driven more by Jupiter's internal heat than by solar energy, highlighting the unique atmospheric dynamics of gas giants. The Sun's activity also has an impact on planetary climates, particularly through solar flares and coronal mass ejections. These events can increase the intensity of the solar wind, which interacts with planetary atmospheres, creating phenomena such as auroras and even stripping away a planet's atmosphere over time. Understanding the sun's role in shaping planetary climates is crucial not only for understanding our own planet, but also for exploring the potential for life on distant worlds. Finally, the tides of Earth's oceans are primarily governed by the gravitational forces exerted by the Moon and the Sun. The Moon's gravitational pull has the most significant effect on Earth's tides, as it is the closest large celestial body to our planet. As the Moon orbits Earth, its gravity causes a bulge of water on the side of Earth facing the Moon, creating what we experience as high tide. Interestingly, there is also a second high tide on the opposite side of the Earth. This is due to the centrifugal force generated by the Earth-Moon system as the Earth rotates. The interaction between the Moon's gravitational pull and this centrifugal force causes a second bulge of water, resulting in 2 high tides and 2 low tides each lunar day. The Sun also plays a role in tidal phenomena, although its influence is less pronounced than that of the Moon. When the Earth, Moon, and Sun align during full moons and new moons, the combined gravitational forces result in particularly high and low tides, known as spring tides. These tides have been observed for centuries and continue to be an area of study for scientists interested in the interplay between celestial bodies and their effects on Earth's oceans. The complex interactions between the Sun, Moon, and Earth provide a rich field for study, offering insights not only into tidal patterns, but also into the broader dynamics that govern life on Earth and potentially on other planets as well. During the first and third quarters of the lunar phase, when the Sun and the Moon align at right angles to Earth, we experience a shift in the tides known as nap tides. These tides are notably lower than the average, marking a period of reduced gravitational pull between the Earth, the Sun, and the Moon. This regular fluctuation is more than just a natural occurrence. It provides a key insight into the deeper mechanics of celestial influence on our planet. Understanding these lunar and solar interactions reveals a hidden world of rhythmic cycles that shape not only the oceans, but the entire ecosystem of our planet. From the smallest tide pools to vast ocean currents, the gravitational dance between Earth and its celestial neighbors dictates patterns that affect marine life, coastal geography, and even the daily activities of humans living by the shore. These tidal forces, which arise from the subtle yet powerful interplay of gravity between the Earth and its cosmic companions, govern much more than just the sea. These celestial events echo the profound principles of Albert Einstein's theory of relativity, a revolutionary framework that reshaped our understanding of space, time, and gravity. The theory is divided into 2 parts: special relativity and general relativity. Special relativity deals with objects moving at constant speeds, and it introduces the groundbreaking idea that the laws of physics remain the same for all observers, regardless of their relative motion. One of its most striking revelations is that the speed of light represents the ultimate speed limit of the universe, fundamentally altering how we perceive the passage of time and the nature of space itself. General relativity, on the other hand, expands on these concepts by explaining gravity not as a force, but as a curvature in space-time. This shift in perspective, where massive objects such as planets and stars warp the very fabric of space and time around them, was a monumental breakthrough in understanding how the universe operates on the grandest scale. As these massive bodies create indentations in space-time, smaller objects are guided along curved paths, a principle that holds true whether the objects are planets, comets, or even light. One of the most profound implications of general relativity is its ability to explain cosmic phenomena, such as gravitational lensing, the bending of light around massive objects like galaxies. This phenomenon enables astronomers to peer into distant corners of the universe, revealing objects and events that would otherwise be hidden from our view. It's not just light that bends in this cosmic dance. The very fabric of time itself undergoes strange distortions. For instance, black holes, regions where gravity is so intense that even light cannot escape, are prime examples of how space and time merge in ways that defy intuition. As objects near these cosmic giants, time itself appears to slow down, an effect known as time dilation. To an observer far from the black hole, this slowing of time seems paradoxical, challenging everything we know about the passage of time and the nature of the universe. General relativity also offers a framework for understanding the expansion of the universe. It is the backbone of the Big Bang theory, providing the theoretical underpinnings that support the idea of a constantly expanding cosmos, where galaxies move away from each other over time. This expanding universe is a reminder of the universe's ever-changing dynamic nature, a vast complex system governed by the laws that Einstein so brilliantly uncovered. In modern astrophysics, simulations have become indispensable tools, allowing scientists to create and study detailed models of cosmic events. By simulating the conditions that existed just after the Big Bang, scientists are able to observe the formation of galaxies and predict the behavior of cosmic structures over billions of years. These simulations provide crucial insights, offering a clearer understanding of processes that are otherwise difficult or impossible to observe directly. They offer a unique way to test existing theories, often supporting them, but also challenging our understanding of the universe. One area where these simulations have proven invaluable is in the study of dark matter, a mysterious substance that we cannot observe directly, but is thought to make up a significant portion of the universe's mass. By incorporating dark matter into their models, astrophysicists have been able to accurately replicate the distribution and clustering of galaxies observed throughout the universe. This supports the hypothesis that dark matter is crucial to the formation and evolution of cosmic structures, playing a pivotal role in shaping galaxies as we see them today. However, not all simulations align perfectly with observational data, and this discrepancy leads to fascinating debates and revisions of existing theories. For example, simulations have suggested that a greater number of small galaxies should have formed in the early universe than what has been observed in galaxies like our own Milky Way. This inconsistency has sparked new investigations into galaxy formation and the role of ordinary matter, known as baryonic matter, in shaping the cosmos. It suggests that current models may need refinement, pushing scientists to reconsider how we understand the birth and development of galaxies. This ongoing interplay between theory, simulation, and observation is a fundamental aspect of scientific progress. Rather than rejecting simulations that don't fit established models, scientists dive deeper into the underlying physics, adjusting their models and refining their understanding of the universe. Each new simulation brings with it new discoveries, both confirming and challenging previous theories, pushing the boundaries of what we know about the cosmos. As our understanding of stellar evolution deepens, new types of stars are being discovered that defy traditional models. Historically, much of our knowledge about stellar evolution has been built around familiar stars like our Sun. However, as we observe more diverse and unusual types of stars, existing theories are being tested and, in many cases, rewritten. These new discoveries may force us to rethink our fundamental understanding of how stars form, evolve, and eventually die, leading to new and exciting breakthroughs in astrophysical research. With every simulation and every new discovery, our picture of the universe grows sharper, more complex, and more beautiful. The cosmic forces that govern the tides and the stars are intricately woven together, shaping not just the physical universe, but also our very understanding of time, space, and existence itself. In recent years, monumental advancements in astronomical research have uncovered an extraordinary range of stellar phenomena, compelling scientists to develop more intricate models that can account for these new complexities. One of the most influential discoveries has been the identification of peculiar stars, such as blue supergiants and hypergiants. These massive celestial bodies challenge our traditional understanding, as they burn through their nuclear fuel at astonishingly rapid rates. As a result, they experience significantly shorter lifespans and follow unique evolutionary paths compared to their smaller counterparts. This revelation has profound implications for our understanding of stellar life cycles. By integrating these extreme cases into existing models, astronomers have been forced to reconsider many long-held assumptions, particularly regarding massive star evolution and the explosive end-of-life events that lead to supernovae. As astronomers work to incorporate these high-energy stars into their models, they are also reevaluating the complex process of how stars evolve and eventually meet their catastrophic ends in supernova explosions. Furthermore, the advent of powerful telescopes and cutting-edge observational techniques has revolutionized our ability to explore previously hidden populations of stars. This includes stars within dense star clusters, as well as those in more exotic and extreme environments. These observations have revealed that stars often interact with one another in unexpected ways, merging, transferring mass, or even siphoning material from their neighboring stars. Such interactions challenge the traditional view of stars as isolated entities and underscore the need for more dynamic and holistic models of stellar evolution, which must now consider factors such as mass transfer, angular momentum, and the influence of nearby stellar companions. As these new discoveries continue to pour in, models of stellar evolution are becoming increasingly sophisticated. Astronomers and astrophysicists now employ advanced computational simulations to capture the nuances of stellar interactions and the role of cosmic elements in shaping a star's ultimate fate. This evolution in our understanding not only broadens our knowledge of stellar life cycles, but also offers new insights into the cosmic landscape in which these stars exist. These insights help illuminate the broader structure of the universe, laying the groundwork for a more comprehensive understanding of the cosmos as a whole. At the heart of this cosmic exploration lies one of the most foundational theories in modern science, the Big Bang Theory. According to this theory, the universe began approximately 13.8 billion years ago from an infinitely dense point. It rapidly expanded, giving birth to both space-time and all the energy that we observe in the universe today. This initial explosive expansion set the stage for the subsequent development of galaxies, stars, and other cosmic structures. Understanding the origins of the universe helps scientists infer how the cosmos might continue to evolve and what its eventual fate could be. As the universe expands, current observations reveal that this expansion is accelerating, driven by a mysterious force known as dark energy. This force suggests that the universe is not simply growing larger, but doing so at an ever-increasing rate. If this trend continues, the universe could ultimately reach a state known as the Big Freeze, where galaxies drift farther and farther apart, stars burn out, and matter becomes increasingly dispersed throughout the cosmos. However, there are alternative outcomes to the universe's expansion, each tied to the fundamental principles of the Big Bang Theory. One possibility is the Big Crunch, a scenario in which the expansion of the universe eventually halts and reverses. This would lead to a collapse, where all matter and energy would condense back into a singularity. While this idea was once widely discussed, it has become less likely based on current observations. The density and energy content of the universe, as measured by modern science, do not strongly support the Big Crunch theory. Another fascinating possibility is the Big Rip, a dramatic and unsettling theory in which the acceleration of the universe's expansion eventually tears apart all structures, galaxies, stars, and even atomic particles. This outcome would result from the increasing repulsive force of dark energy, which could eventually overcome all other forces in the universe. While these theories may seem speculative, they illustrate how the Big Bang Theory not only helps us understand the origin of the universe, but also provides a framework for predicting its distant future. As our understanding of cosmology deepens, the Big Bang Theory remains central to guiding our comprehension of the universe's past, present, and potential futures. Different cosmological models, based on general relativity and calculations of the universe's density and energy content, offer a variety of predictions about its ultimate fate. For example, models based on the universe's critical density, an essential concept in cosmology, propose that if the universe's density exceeds a certain threshold, gravitational forces could reverse the expansion, eventually leading to a collapse. On the other hand, if the universe's density falls below this critical value, the Big Freeze scenario becomes more likely. In this model, the universe would continue expanding forever, eventually growing cold, dark, and sparse as stars burn out and galaxies drift apart. These models are further complicated by the influence of dark energy, which introduces the possibility of the Big Rip. As dark energy pushes outward with ever-increasing force, it could tear apart not only galaxies and stars, but also planets, atoms, and even the fundamental building blocks of matter. The varying cosmological models we explore highlight the delicate balance between gravity, energy, and the structure of the universe. These models underscore the many mysteries that remain in our understanding of the cosmos. As observational technologies continue to improve, scientists are refining these models, continuously testing our knowledge and exploring new implications for the universe's behavior. Every new discovery challenges existing frameworks and pushes us closer to answering the question, what will ultimately become of the universe? Beyond the realm of individual stars and galaxies, astronomers have also uncovered intriguing new patterns in the process of star formation itself, patterns that defy traditional models. One such discovery involves starburst galaxies, which undergo rapid, intense bursts of star formation. In these galaxies, hundreds or even thousands of new stars can form in just a few million years, a blink of an eye in cosmic terms. Starburst events are often triggered by external factors such as galaxy collisions, which compress vast amounts of gas and dust, igniting new stars in a frenzy. Another remarkable observation involves the dense cores within molecular clouds, where conditions are particularly conducive to star formation. In some of these dense regions, entire clusters of stars form together, rather than isolated stars. These stellar nurseries, bound by the mutual gravitational attraction of their constituent stars, offer a fascinating glimpse into the collaborative nature of star birth. A striking example is the Orion Nebula, where a rich cluster of young stars is currently forming in a small, highly concentrated region of space. This cluster is so intense that it illuminates the surrounding gas and dust in breathtakingly beautiful ways. Equally surprising are the discoveries of solitary stars that form in isolation, far from the denser regions of galaxies. These stars are born in the cold, sparse interstellar medium, where conditions for star formation are far from ideal. The existence of these solitary stars challenges the long-held notion that all stars must form in clusters, and suggests that the universe offers a far broader range of environments that are conducive to star birth than previously imagined. These remarkable discoveries continue to reshape our understanding of how stars are born, evolve, and ultimately meet their ends. As astronomers push the boundaries of observation, the very nature of stars and their origins is being redefined, offering new insights into the fundamental processes that shape our universe. Astronomers have uncovered a fascinating phenomenon in the cosmos: runaway stars. These are stars that, despite originating in the dense heart of bustling star clusters, are ejected into the vast emptiness of interstellar space. The process unfolds through gravitational interactions, where these stars, once part of a thriving stellar nursery, find themselves flung far from their birthplace. As they venture through the void, they become solitary, shining beacons in the immense expanse of space, far from the familiar cradle where they were born. This strikingly rare and unusual pattern in star formation is a vivid reminder of the complexity and unpredictability of the cosmic process. The very nature of how stars form continues to puzzle and captivate astronomers, presenting them with mysteries that seem to stretch beyond the limits of our understanding. The stillness of space offers yet another layer of intrigue. In the vastness of the cosmos, there is no sound. This silence can be traced back to the very essence of sound itself. It needs a medium, such as air or water, to carry waves. However, space is a vacuum, and in the absence of particles that can vibrate to propagate sound waves, there is no audible noise. As we gaze up at the stars, this absence of sound, far from being merely unsettling, provides a sense of deep perspective. The sheer immensity of the universe forces us to confront our place within it, highlighting the insignificance of our everyday concerns in the grand scheme of the cosmos. The silence we experience, though profound, inspires awe and curiosity, prompting us to delve deeper into the mysteries that lie beyond our world. It invites us to contemplate not only what exists beyond the stars, but also what it means to be part of this grand cosmic narrative. However, the quiet of space does not mean a lack of communication. In the absence of sound, the universe speaks to us in other ways, through electromagnetic radiation. The cosmos sends us signals in the form of visible light, radio waves, and gamma rays. These signals, captured by telescopes and instruments both on Earth and in space, serve as our means of understanding the cosmic events unfolding across vast distances. When a star explodes in a supernova or when two neutron stars collide, the resulting waves of energy travel through space, carrying with them valuable information. Though these cosmic events unfold in silence, the data they produce is anything but mute. Scientists decode these signals, translating them into meaningful insights about the nature of the universe. The cosmic silence, instead of being a void, becomes a rich tapestry of hidden knowledge, waiting to be discovered through our technology and curiosity. This drive to uncover the mysteries of the cosmos is not new. Throughout history, humanity has meticulously recorded astronomical phenomena, shaping our current understanding of the universe. Ancient civilizations, such as the Babylonians and the Chinese, were among the first to document celestial events. They recorded the movements of the stars, the occurrence of solar eclipses, and even planetary alignments. These observations were not merely for record-keeping, but provided invaluable data that allowed future generations to map the heavens, predict celestial events, and understand the rhythm of the cosmos with remarkable accuracy. One striking example of such historical documentation is the supernova recorded by Chinese astronomers in 1054 CE. This stellar explosion was so bright that it could be seen in broad daylight for weeks. The Chinese meticulously documented this event, and centuries later, when scientists discovered the remnants of the supernova, they realized it was a crucial piece in understanding the life cycle of stars and the violent nature of stellar explosions. This particular supernova marked a pivotal moment in the study of stellar evolution, showing how ancient records can serve as keys to unlocking the secrets of the universe. Moreover, historical accounts of comets too have enhanced our knowledge of the cosmos. One of the most famous celestial visitors is Halley's Comet, which has been observed for thousands of years. Its return was noted in various cultures, and through careful observation, astronomers have been able to calculate its orbit, determining that it passes through our solar system approximately every 76 years. These ancient observations, passed down through generations, have allowed modern scientists to track the comet's movement with incredible precision. The periodic appearance of Halley's Comet is a testament to the continuity of human curiosity and understanding, spanning millennia. It reflects our shared endeavor to comprehend the vastness of the universe and to chart its cycles, demonstrating how ancient wisdom continues to inform contemporary science. In this ongoing journey to understand the cosmos, the past and present are intricately linked. The historical records left behind by ancient astronomers serve as a bridge between millennia, connecting the ancient world to modern-day exploration. These observations not only provide a deeper understanding of celestial mechanics, but also help scientists piece together the intricate history of our universe. Each new discovery builds on the knowledge passed down through the ages, creating a rich, collective tapestry of human endeavor to explore the stars. Despite the silence of space, this quest for understanding resounds loudly through our curiosity, our tools, and the profound sense of wonder that drives us to continue exploring the cosmos. Throughout history, the observation and recording of celestial events have profoundly shaped human culture and belief systems. Eclipses, comets, and planetary alignments have long been viewed as omens or messages from the divine, reflecting humanity's deep connection with the cosmos. These ancient records, etched in stone and ink, serve as windows to a past where the sky was more than just a backdrop to daily life. It was a realm of mystery, power, and divine influence, a constant source of wonder, inspiration, and fear. By studying these records, we not only uncover the secrets of the universe, but also witness how human understanding and curiosity about the heavens have always been intricately woven into our cultural and spiritual fabric. Each of these artifacts is a testament to our unyielding quest for meaning and connection beyond our earthly existence. In ancient civilizations, astronomy was far more than a scientific discipline. It was intimately tied to religion, agriculture, and governance. The Maya, renowned for their profound knowledge of the stars, are a prime example. They constructed sophisticated observatories like the one at Huaxactún in Guatemala, designed to track the movements of celestial bodies. The Mayas' meticulous observations of the heavens, ranging from the motions of planets and stars to the appearances of comets, were not merely academic pursuits. They directly influenced practical aspects of life, such as agricultural cycles and religious rituals. Their calendar system, the Hab, was astonishingly accurate, guiding everything from planting crops to scheduling important religious ceremonies. This harmony between the celestial and terrestrial worlds underscores the Maya belief that the cosmos played an active role in shaping human fate. A similar reverence for celestial bodies is evident in the prehistoric site of Stonehenge in England. This massive stone circle, whose origins stretch back thousands of years, aligns with significant astronomical events, including the solstices and lunar phases. Researchers speculate that Stonehenge may have served as a site for religious ceremonies, where ancient people gathered to honor the cycles of the sun and the moon. The precision with which the monument aligns with solar and lunar movements speaks to a profound understanding of celestial cycles and their importance in both spiritual and practical life. As such, Stonehenge stands as a powerful symbol of how the ancient world blended spirituality with scientific observation, seeking to understand not only the physical universe, but also humanity's place within it. The ancient Greeks, too, made significant strides in connecting the heavens to earthly life, as evidenced by the discovery of the Antikythera mechanism in 1901. Found in the wreck of a ship off the coast of Greece, this remarkable device is often described as the world's first analog computer. With its intricate gears and precise engineering, the mechanism allowed the ancient Greeks to calculate the positions of celestial bodies and predict astronomical events with extraordinary accuracy. This device is a testament to the intellectual curiosity of the ancient world, a curiosity that sought to understand the cosmos in a way that was not just mystical, but deeply rational and mathematical. The Antikythera mechanism demonstrates how early civilizations sought to bridge the gap between the heavens and the earth, grounding celestial phenomena in human experience. Similarly, the ancient Egyptians built the Great Pyramids with a clear alignment to the cardinal points of the compass. These colossal structures were designed not only as tombs for pharaohs, but also as representations of the divine order of the universe. The pyramid's orientation likely corresponds to the rising of certain stars, such as Sirius, which had profound religious significance for the Egyptians. For them, the stars were not distant and unrelated objects, but intimately connected to their beliefs about life, death, and the afterlife. The precise alignment of the pyramids reflects their deep understanding of the cosmos and their belief that the stars played a central role in both earthly and divine affairs. In the 20th century, a new chapter was added to the story of humanity's search for meaning in the cosmos with the discovery of the WOW signal in 1977. This enigmatic radio signal, which lasted for just 72 seconds, was unlike any other ever recorded. It came from a region of space that, at first glance, seemed devoid of nearby stars, leading some to speculate that its origins could be artificial in nature. This single, unexplained signal has sparked decades of research and speculation about the possibility of extraterrestrial life. Despite the lack of further detections, the WOW signal remains one of the most compelling pieces of evidence in the ongoing quest for intelligent life beyond Earth. In the wake of the WOW signal, scientists and astronomers have intensified their efforts to scan the cosmos for similar signals. The Search for Extraterrestrial Intelligence, SETI, an initiative that seeks to detect radio waves or other forms of communication from distant civilizations, has grown in scope and sophistication. Modern technology, including high-powered telescopes and advanced algorithms, allows researchers to sift through vast amounts of data, looking for signals that may mirror the mysterious characteristics of the WOW signal. Yet, as the search intensifies, researchers are confronted with a new challenge: the vastness of the universe. The sheer amount of background noise from cosmic radiation makes it difficult to isolate signals that might indicate intelligent life. This has prompted scientists to develop more targeted search strategies, focusing on specific regions of space where conditions might be more favorable for intelligent life to emerge. The WOW signal, though still a singular event, continues to inspire both the scientific community and the general public. its legacy lies not only in its mysterious origins, but also in its ability to spark curiosity and speculation about our place in the universe. The possibility that the universe may be filled with intelligent civilizations waiting to be discovered remains a tantalizing thought. As humanity pushes further into the cosmic frontier, each technological breakthrough brings us closer to answering the question that has captivated our imaginations for centuries: are we alone in the universe? One area of technological innovation that promises to make the dream of interstellar travel a reality is the development of advanced propulsion systems. Traditional rocket engines, which rely on expelling mass to generate thrust, are limited by the amount of fuel they can carry and the distances they must travel. As a result, these systems are insufficient for the vast distances between stars. However, recent developments in propulsion technology have the potential to change this. Ion propulsion, for example, utilizes electric fields to accelerate ions, providing a highly efficient means of propulsion. This system allows spacecraft to carry less fuel while still achieving considerable speeds, making it a promising option for missions to distant celestial bodies or even for low-orbit travel. Nuclear thermal propulsion is another breakthrough that could revolutionize space travel. This technology uses nuclear reactions to heat a propellant, producing thrust far greater than that of conventional chemical rockets. If successful, nuclear thermal propulsion could shorten travel times within our solar system and pave the way for missions to the outer reaches of space. For even greater speeds, researchers are exploring nuclear pulse propulsion, a concept that involves detonating nuclear devices behind a spacecraft to propel it forward. Though still in the theoretical stages, this method could potentially allow a spacecraft to travel at a significant fraction of the speed of light, opening up the possibility of reaching distant star systems within a human lifetime. One of the most innovative concepts is the use of light sails, which rely on the pressure exerted by photons, either from the sun or from a powerful laser, to propel a spacecraft across vast distances. Projects like the Planetary Society's Light Sail and the proposed Breakthrough Starshot initiative envision small, lightweight probes that could be accelerated to substantial fractions of the speed of light using ground-based or orbital lasers. This revolutionary idea holds the promise of sending spacecraft to nearby stars, like Alpha Centauri, potentially within the span of a human lifetime. As these technologies evolve, they bring humanity ever closer to the day when the stars may no longer be out of reach, and the dream of interstellar travel becomes a reality. Antimatter propulsion research explores the intriguing possibility of harnessing antimatter as a powerful fuel source for space travel. At the core of this concept lies the process of antimatter annihilation, a reaction that releases a staggering amount of energy. This immense energy could theoretically be used to propel spacecraft, potentially enabling us to reach far beyond the boundaries of our current capabilities. However, while the potential is vast, the creation and containment of antimatter remains some of the greatest hurdles. The need for extreme precision and conditions far beyond what we can presently achieve makes it a monumental challenge. Yet, despite these obstacles, the idea continues to fuel scientific curiosity, offering tantalizing glimpses of a future where interstellar travel might become a reality. Each step in this research is not just a technical leap, but also a step forward in understanding the very nature of the universe. The potential for antimatter propulsion could revolutionize space exploration, offering us a means of travel that could one day make intergalactic journeys feasible. The road to realizing this dream, however, remains long and uncertain, but the possibilities inspire immense interest in the scientific community. In parallel with these cutting-edge propulsion concepts, advancements in telescope technology have dramatically transformed our ability to observe the cosmos. The universe, once a vast and impenetrable mystery, is now becoming an open book. By expanding our observational capabilities, we have unlocked new avenues of discovery, and our understanding of distant celestial objects has undergone a profound shift. Modern telescopes, equipped with state-of-the-art instruments, are now capable of probing deeper into the universe than ever before. One of the most exciting breakthroughs in this field is the advent of adaptive optics, a technology that compensates for the distortions caused by Earth's atmosphere. This innovation has led to clearer, more detailed images of distant stars, galaxies, and nebulae, giving astronomers unprecedented views of the cosmos. But the improvements don't stop there. The sheer size and power of modern telescopes allow them to collect more light and focus on fainter, more distant objects, expanding our ability to study the farthest reaches of the universe. Beyond Earth's atmosphere, space-based telescopes like the Hubble Space Telescope have completely transformed astronomical observation. These instruments operate in the vacuum of space, free from the distortions of the atmosphere, capturing images with unparalleled clarity. Furthermore, space telescopes can observe a broader range of wavelengths, including ultraviolet and infrared light, enabling the study of celestial phenomena that would otherwise be invisible. These capabilities are essential for understanding the early universe, where much of the radiation emitted by stars and galaxies lies outside the visible spectrum. As we continue to push the limits of space observation, future missions like the James Webb Space Telescope promise even more exciting discoveries. Designed to peer deeper into space than ever before, this mission aims to uncover the mysteries of the first stars and galaxies that formed after the Big Bang. By peering into the distant past, we hope to better understand the origins of the universe and the forces that have shaped its evolution over billions of years. With each technological advance, our understanding of the universe grows ever more refined. These telescopes are not just capturing images, they are unlocking the history of everything, from the formation of galaxies to the birth of stars. Every new breakthrough strips away another layer of cosmic history, bringing us closer to understanding the complex and ever-changing nature of the universe. In parallel, the realm of data collection and analysis in astronomy has been transformed by recent advancements in technology. Large-scale observatories, equipped with cutting-edge sensors, are now capable of capturing an immense amount of data across multiple wavelengths, from visible light to radio waves and infrared radiation. These instruments are transforming our ability to study the cosmos, revealing objects and phenomena that were once undetectable with earlier equipment. As part of this transformation, sophisticated data analytics tools, particularly those based on artificial intelligence and machine learning, are playing a central role. These algorithms are capable of processing vast amounts of data in record time, identifying patterns that would be nearly impossible for traditional methods to uncover. For example, machine learning is being used to sift through enormous datasets from astronomical surveys to detect unusual events such as supernovae or the presence of exoplanets. By analyzing subtle variations in light, AI is accelerating the discovery of these phenomena and offering new insights into the workings of the universe. The impact of these technologies is not limited to the distant stars. Space probes and rovers, which explore the planets and moons of our own solar system, are providing invaluable data that informs our understanding of planetary science. These instruments gather real-time information about planetary atmospheres, surface composition, and the presence of water or ice, key factors in determining the potential for extraterrestrial life. The data sent back to Earth from these missions enriches our knowledge of planetary formation and the conditions that might support life beyond our planet. As we continue to refine the tools and techniques for studying the cosmos, our understanding deepens, but so too do the questions that drive further exploration. Each discovery uncovers new mysteries, encouraging scientists to venture even farther into the unknown. The pursuit of knowledge about space remains an ongoing journey, one that constantly challenges our imagination and pushes the boundaries of what we know. Meanwhile, three-dimensional printing technology is proving to be a game changer in space exploration. This innovative tool is providing practical solutions to some of the unique challenges that arise in space missions. The ability to print components and tools on demand directly in space eliminates the need to transport heavy and costly payloads from Earth, which is particularly important given the high cost of space travel. By enabling the on-site fabrication of parts, three-dimensional printing enhances the flexibility and efficiency of missions. It allows engineers to create components tailored to specific mission requirements, resulting in lighter, stronger, and more durable materials designed to withstand the extreme conditions of space. NASA has already begun integrating this technology into its space missions, with one notable example being the printing of rocket engine components designed to endure the harsh realities of space travel. One of the key advantages of three-dimensional printing is its ability to rapidly prototype and test new designs. This capacity for fast iteration speeds up the process of innovation, allowing engineers to make real-time adjustments and improvements to their designs without the delays typically associated with traditional manufacturing processes. As this technology continues to evolve, it holds the potential to significantly reduce costs and enhance the adaptability of future space missions, further enabling humanity to explore the farthest reaches of our solar system and beyond. The journey of discovery continues to unfold, driven by technological advancements that are pushing the boundaries of what we thought was possible. As we advance in our understanding of the universe and develop new tools to explore it, the future of space exploration grows ever more promising. As space missions extend to longer durations, particularly those aimed at Mars, the need to create self-sustaining systems becomes more urgent. One promising technology gaining attention is three-dimensional printing. This technology can revolutionize the way we produce essential resources like food and shelter using local materials available on celestial bodies. Researchers are increasingly focused on how to utilize materials such as lunar and Martian regolith, the dust and rock particles found on the surfaces of the Moon and Mars, to fabricate construction materials or even life support systems. This innovative approach could dramatically reduce humanity's reliance on constant supply chains from Earth, paving the way for more autonomous missions. With the goal of supporting sustainability, three-dimensional printing offers immense potential in constructing habitats, repairing equipment, and even producing tools or other resources in space. Imagine astronauts building entire colonies on distant planets, not relying on Earth for every single need. In fact, the technology may one day make it possible to not only build homes on alien worlds, but also to address unforeseen challenges in real time, reducing the need for costly and time-consuming returns to Earth for repairs. The possibilities are endless, and this breakthrough exemplifies how cutting-edge technology can open up new frontiers for human exploration, colonization, and survival beyond our home planet. As this technology evolves, the future of space exploration will see even more advanced forms of three-dimensional printing that could further revolutionize our ability to establish a human presence on other worlds. Whether it's building habitats on Mars or producing fuel or equipment for long-term missions, this transformative approach will be at the heart of making space exploration both sustainable and feasible for future generations. Moreover, the success of these missions and technologies will rely heavily on international cooperation. Space exploration is an inherently complex endeavor that demands the collective effort of nations pooling their resources, expertise, and technologies. No single country, no matter how advanced, can shoulder the immense financial and logistical burden of space missions alone. By joining forces, nations can share both the costs and the risks associated with ambitious space projects, enabling them to push the boundaries of what's scientifically possible. Such collaborations not only make ambitious missions more achievable, but also lead to faster advancements in space science and technology. When scientists, engineers, and experts from diverse backgrounds work together, they bring unique perspectives and ideas that can result in unexpected breakthroughs. One of the best examples of this international spirit of cooperation is the International Space Station, ISS. The ISS is more than just a floating laboratory. It's a symbol of what can be accomplished when countries set aside differences and unite for the shared goal of exploration and discovery. The data and knowledge generated by the ISS benefit all its participating nations, driving progress in fields like human physiology in space, material science, and environmental monitoring. In addition to advancing scientific understanding, these international collaborations have a profound impact on global diplomacy and policy. Through joint space missions, countries are able to establish guidelines and agreements regarding the peaceful use of outer space. This not only reduces the likelihood of conflict, but also promotes mutual trust and understanding among nations. As more countries enter the space race, this spirit of cooperation becomes increasingly essential, especially when it comes to managing the complex geopolitical dynamics of space exploration. The increasing collaboration among countries in space exploration is shaping the future of space science in profound ways. It accelerates progress, ensures that outer space remains a shared human endeavor, and encourages future generations to look beyond Earth, fostering a sense of collective responsibility for the future of humanity. The success of these international missions will undoubtedly inspire future explorers and innovators to continue pushing the limits of what is possible. However, the journey ahead is not without its challenges. One of the most pressing issues facing future missions is the growing problem of space debris in Earth's orbit. As the number of satellites, rocket stages, and fragments from past collisions increases, so does the risk posed by this debris to operational spacecraft. Traveling at incredible speeds, even a tiny fragment of debris can cause catastrophic damage to a satellite or spacecraft. This presents an enormous risk to the infrastructure we rely on for everything from telecommunications to weather monitoring to global navigation systems. The economic impact of this growing problem is equally significant. The risk of collisions in orbit could lead to service disruptions that affect billions of people around the world. If critical satellites are damaged or destroyed, the resulting loss of communication, weather forecasting, or navigation capabilities could cost countries and companies billions of dollars. As the volume of space debris continues to increase, the potential for such collisions and the resulting damage grows more likely. Addressing this issue will require innovative solutions, including the development of new technologies to safely remove or mitigate the risk posed by space debris, as well as international agreements to regulate and manage space activities more effectively. The challenges posed by space debris highlight the need for continued collaboration and innovation in space exploration. As the number of countries and private entities entering the space industry grows, so too does the need for clear guidelines and technologies to ensure the long-term sustainability of space activities. Only through collective action and shared responsibility will we be able to overcome the hurdles of space debris and continue to explore, discover, and thrive in the final frontier. Space exploration has long captured the human imagination, igniting a profound desire to reach beyond our world and explore the unknown. However, as we continue to expand our presence in space, we are confronted with a growing and pressing issue: space debris. While the cosmos offers endless opportunities for discovery, the remnants of past missions have created a perilous landscape just beyond Earth's atmosphere. As these particles collide and fragment, they multiply, creating a dangerous chain reaction known as the Kessler syndrome. In this scenario, one collision leads to more debris, which leads to further collisions, each multiplying the risk. The resulting environment is one where space travel becomes increasingly hazardous, with certain orbits potentially rendered unusable for generations. This growing problem isn't just an abstract concern, it has real-world implications for the safety and viability of future space missions. Adding to the complexity of this challenge is the difficulty of tracking smaller fragments of debris. While larger pieces can be monitored and potentially removed, the countless tiny particles that now populate space remain largely invisible to existing tracking systems. Current debris cleansing technologies are still in their infancy, unable to effectively address the scale of the problem. This is compounded by the global nature of space exploration. There is no single nation or entity responsible for all space activities, making international collaboration essential. Addressing this issue will require unprecedented cooperation, as well as the development of new technologies to monitor, mitigate, and eventually remove debris. Yet, as we confront the growing threat of space debris, we also find ourselves facing new challenges and opportunities in the realm of technological advancement. Space missions have historically been catalysts for progress, driving innovation that often finds its way into everyday life. For example, the harsh conditions of space travel have led to the development of materials that can withstand extreme temperatures, radiation, and the vacuum of space. These materials, originally designed for use in spacecraft, have been adapted to industries on Earth, including construction, electronics, and consumer goods. The result is a new generation of lighter, stronger, and more durable materials that benefit not just space missions, but also our everyday lives. One of the most profound impacts of space exploration has been in the field of medical technology. Advances in imaging and diagnostic tools that were initially developed for space missions have revolutionized healthcare on Earth. Magnetic resonance imaging, MRI, and computed tomography (CT) scans, for example, were refined through space research to meet the needs of astronaut health monitoring. These same technologies are now essential in diagnosing and treating patients around the world. The need to ensure astronaut well-being in the harsh environment of space also spurred innovations in telemedicine, which now allows doctors to conduct remote consultations and provide diagnoses to patients, even in the most remote corners of the Earth. Satellite technology, developed for space missions, has also had a transformative effect on life on Earth. GPS, weather forecasting, disaster response, and environmental monitoring all rely on satellite data. These technologies, which were perfected in the vacuum of space, have become integral to modern life. In particular, satellite-based systems have revolutionized global navigation, enabling everything from driving directions to the precision of military operations. The ability to monitor the Earth's climate from space has also opened new frontiers in climate science, offering insights into our planet's health and providing tools to protect it. But as humanity ventures further into the cosmos, the need for sustainability has never been more critical. The challenges of protecting Earth's environment extend beyond our planet. Scientists and engineers are now working to develop strategies that allow us to explore space without jeopardizing future opportunities or damaging celestial environments. One promising concept is in situ resource utilization, which encourages the use of local materials found on other planets or moons for building structures and sustaining human life. For example, using the materials found on the moon, such as regolith, to construct habitats would significantly reduce the need for costly and wasteful transportation from Earth. This approach could not only make space exploration more sustainable, but also open the door to long-term human habitation beyond our home planet. Another key focus is reducing the ever-growing problem of space debris. As we expand our presence in space, debris poses a serious risk to spacecraft, satellites, and astronauts. In response, scientists are developing innovative solutions to actively remove debris. From nets and harpoons to laser technology designed to deorbit defunct satellites, these technologies aim to clean up the remnants of past missions and ensure a safer environment for future explorers. By prioritizing the management and reduction of space debris, space agencies are taking a responsible approach to exploration, ensuring that we don't simply exploit space, but also preserve it for generations to come. In this new era of space exploration, humanity must learn to balance progress with sustainability. The technologies and advancements sparked by space missions not only enhance our understanding of the universe, but also improve life on Earth in ways we may never have imagined. Yet, as we continue to push the boundaries of what is possible, we must also consider the long-term impact of our actions. Only through responsible exploration and global collaboration can we ensure that space remains a resource, not a hazard, for future generations of explorers. The realm of space exploration is undergoing a profound transformation as scientists and engineers venture beyond the conventional boundaries of technology. In recent years, a growing focus has emerged on the potential of propulsion systems that harness renewable energy sources. Unlike traditional chemical rockets, which are both costly and environmentally damaging, these new concepts, such as solar sails and ion propulsion, offer cleaner and more sustainable alternatives. The goal is not just to reduce the ecological footprint of space missions, but to develop technologies that minimize harmful emissions, enabling us to explore space with a greener, more responsible approach. Space missions, whether they are aimed at low Earth orbit or far-reaching destinations in the depths of space, have long relied on chemical propulsion systems that consume vast amounts of fuel. These systems, while effective, come with significant environmental costs, from the carbon emissions generated by rocket launches to the waste produced during the mission itself. The environmental impact has been a subject of increasing concern. By investing in cleaner propulsion systems, we have the opportunity to drastically reduce the harmful byproducts of space exploration. Innovative technologies such as solar sails, which use the pressure of sunlight to propel spacecraft, or ion propulsion, which uses electrically charged particles for efficient thrust, represent promising solutions. These systems, powered by renewable energy, could dramatically decrease the need for chemical fuels, cutting down on emissions and costs. As these technologies evolve, they will not only make space travel more sustainable, but could also open the door to new possibilities for human exploration of distant worlds. Collaboration plays a pivotal role in realizing these advancements. Education and international cooperation among space agencies, private companies, and research institutions are essential for fostering sustainable practices. By sharing resources, expertise, and knowledge, these entities can work together to develop best practices and set global standards for space exploration. This unified approach will ensure that space exploration is not solely about competition or the race for resources and prestige, but about a collective responsibility to protect and responsibly expand humanity's presence in the cosmos. These partnerships among countries and corporations will allow for the creation of agreements that prioritize sustainability, not just in terms of propulsion, but also regarding environmental protection in space. By sharing ideas, technology, and strategies, the global space community can move toward more eco-friendly methods of exploration. Taking these steps now, while still in the early stages of space exploration, is crucial for laying the groundwork for a sustainable future in space. This will allow humanity to tap into the wonders of the universe without jeopardizing its future generations. One critical aspect of this responsible exploration is planetary protection, a growing field of study focused on preventing biological contamination as we explore other worlds. The need for planetary protection grows as we send increasingly sophisticated missions to distant celestial bodies like Mars, Europa, and beyond. When we dispatch spacecraft to these alien worlds, we must ensure that they are free of Earth-based microorganisms that could inadvertently contaminate local ecosystems or interfere with scientific investigations. Planetary protection is not just about safeguarding the integrity of the environments we explore. It also ensures that the scientific data we collect is pure and undistorted by the introduction of Earth-based life forms. If we were to unknowingly introduce microbes from Earth to another planet, these organisms could disrupt the natural conditions, making it difficult or even impossible to study the true state of these environments. This concept is governed by strict guidelines designed to minimize the risk of contamination. Missions to planets like Mars, where there is potential for subsurface water or past microbial life, require rigorous sterilization protocols. Spacecraft materials must be meticulously cleaned, and some are even subjected to high-temperature treatments to eliminate any remaining microorganisms. Similarly, missions to icy moons like Europa and Enceladus, which are believed to harbor subsurface oceans, are subject to even more stringent protocols due to the possibility of life existing beneath their frozen surfaces. The public interest in these missions is immense, as the allure of discovering extraterrestrial life and understanding other planetary environments captures the human imagination. However, understanding the concept of planetary protection is vital not only for scientific progress, but also for the ethical considerations that accompany our exploration. The preservation of other worlds' ecosystems is paramount, and as stewards of the universe, we must ensure that our pursuit of knowledge does not come at the expense of potentially discovering new forms of life or understanding the true nature of these distant environments. By adhering to planetary protection guidelines, we demonstrate a sense of respect for the delicate balance of life, whether on Earth or on other planets. These protocols guide our actions as we explore, ensuring that our scientific curiosity does not inadvertently harm the very environments we wish to study. The future of space exploration will depend on finding this balance between discovery and caution as we continue to push the boundaries of our understanding of the universe. The importance of planetary protection extends beyond ethical considerations. It also provides vital lessons about our role as explorers. Every mission we undertake, every step we take toward understanding the cosmos, teaches us more about our own responsibility to protect and preserve the Earth. As we prepare for future missions, the principles of planetary protection will remain a cornerstone of our approach to exploration, allowing us to pursue knowledge while respecting the intricate balance of life beyond our own planet. In addition to the quest for extraterrestrial life, the exploration of other planets offers profound insights into the challenges we face on Earth. By observing the atmospheres, weather patterns, and geological processes of distant worlds, we can gain a deeper understanding of the forces that shape planetary environments. For example, the atmosphere of Venus provides a stark warning about the dangers of unchecked greenhouse gas emissions. The thick, toxic clouds that envelop the planet trap heat, resulting in surface temperatures that exceed 800 degrees Fahrenheit, far hotter than anything experienced on Earth. This extreme greenhouse effect serves as a chilling reminder of what could happen to our own planet if climate change is left unchecked. Mars offers another compelling case study. Once a world with flowing water and a thicker atmosphere, Mars has since undergone drastic changes that have transformed it into the cold, dry desert we see today. Understanding how Mars transitioned from a potentially habitable planet to its current state underscores the fragility of planetary climates and the potential for rapid environmental shifts. It is a powerful reminder that even slight changes in a planet's atmosphere can have profound and irreversible consequences. Similarly, the gas giants Jupiter and Saturn provide a window into the dynamics of weather systems on a grand scale. The Great Red Spot, a massive storm on Jupiter, has been raging for centuries, demonstrating not only the resilience of weather patterns, but also the potential for long-lasting climatic phenomena. Studying such systems helps scientists understand Earth's weather dynamics and provides insight into how climate change could affect our own planet. By analyzing the atmospheric behavior of other worlds, we can draw parallels to Earth's weather and gain a better understanding of how our climate may evolve in the face of human activity and natural forces. The exploration of other planets is not only a pursuit of knowledge, but a critical tool in understanding the delicate relationship between a planet's atmosphere and its ability to sustain life. The lessons learned from these worlds provide invaluable information that can inform our efforts to combat climate change here on Earth. By studying other planetary environments, we gain a clearer picture of the challenges we face in maintaining a habitable climate, and we are reminded of the urgent need to act before irreversible damage is done. Ultimately, the exploration of space and the study of distant planets offers more than just the potential for scientific breakthroughs. It provides essential insights into the health of our own planet, the fragility of life, and the complex interplay between climate and habitability. As we continue our journey into the cosmos, these lessons will guide our actions, ensuring that we not only expand our knowledge, but also protect the future of our own world.